Yeah. Good morning, all. Good morning to all. Am I audible? Hello? Yes. Okay. Thank you. Thank you. Good morning. Yeah. So welcome to the fourth day of the crash course. So today we'll start with module 5, right? So this is one of the modules which requires the prerequisites of all the previous modules, that is module 2 also necessary and module 4 necessary. Module 3, it's okay, but module 2 and module 4 are very much necessary for this module 5. But once you know the concepts, you need not prepare. You just have to know the steps and the concepts, right? So we'll start off with module 5. So these are the topics of module 5. Registers and counters are the main topics. Under that you have registers and register transfers, parallel adder with accumulator, shift registers, design of binary counters, counters for other sequences, counter design using SR and JK flip-flops. Then you have sequential parity checker, state tables and graphs. So this module requires SR and JK, which is there in module 4, and module 2 for design of counters. You need to know the K-map grouping and writing the equation. So, right. So for this SR and JK, for this counter design, you need the knowledge of both module 2 and module 4, right? So we'll go to the first slide. So first topic is registers and register transfers. So first of all, we should see what is a register. Does anyone know what is a register? Can anyone answer? I have not defined here actually, but if anyone knows, you can answer. What is a register? Good. Collection of flip-flops, group of flip-flops. Very, very correct. So register is nothing but a group of flip-flops connected in a particular way, right? So in the registers, we have different types, which will be covered later by Shalini ma'am. So here, this is one of the connections shown for a register. So how many bit register is this? In the register, you will have the number of bits. How many bits is there in this particular register? 4 bits. Very good. So this register has 4 flip-flops, hence it is of 4 bits. So as many flip-flops you have, the register will be of so many bits. So that is what is given here. Each flip-flop can store 1 bit of binary information. So this register can store 4 bits of information. And this register has a load signal which is ANDed with the clock. So here you can see the load signal, right? This is the load signal. One second. So here you have the load signal. This is connected with the clock. Connected means it is ANDed with the clock. So clock, when both are active, when both are high, only then here it will be high. Otherwise, this output will be 0. So hence, whenever we want the data to be loaded, at that particular time, we will make load as high. So the next clock pulse will also be high. So at that time only this will be high. Only then whatever data is present here can be loaded into the register. So this load is for, the AND gate is for connecting load signal and clock signal for activation of the data loading. So why we use this is, suppose at times we want to retain the current data, right? At particular situations, we may need to have the current data for some duration, right? So after that, we may store the next information. So at such situations, we need this load to be ANDed with the clock. So if you don't have this load signal, what happens is, for the next clock pulse, whatever data you give here, that will be stored into the register. But for the next clock pulse also, we don't want this data to be stored here. We want the previous data. So when we want to store the previous data or continue with the previous data for some more time, then we, at such applications, we need to have this AND gate, which has the input of load and clock. So that is called as gated clock. So this is called as gated clock, right? So when we need gated clock is whenever we need a data present in the register. When the data present in the register has to be used for some more duration, then we may need this gated clock. So how it works is again explained here. When load equals 0, right? So here when load is 0, the register is not clocked because the AND gate output will be high only if load and clock both are 1. But here, as you see, load is 0. Even if clock is 1, 1 means based on this required signal, right? Clock will be, even the clock is 1, the output will not be 1. So whenever you have load as 1, only then the output of AND gate will be 1, and whatever data is present here can be stored into the register. So this can be stored into the register only when load is and of load signal or the application of gated clock. Why do we need a gated clock? Suppose the previous data was 0. So I wanted to continue with the 0, 0, 0 for say 4 or more clock pulses. So after that only I want the current data to be entering into the, to be stored into the system. So at such situation, I will use a gated clock, right? So whenever we want to continue with the current data, then we go for gated clock. If you don't have the gated clock, then whenever the clock changes, and if we give a input, if suppose the next input was 1, 0, 1, 1, I would have given the next input here, but still I want to continue with this previous input. The previous data only I have to continue. I need to continue. I don't want the next data to be entered in the next clock pulse. So what I have to do is I have to use a gated clock. Understood? What is the application or what is the use of gated clock? Ma'am, what is load input? But ma'am, inverted clock is used. So if the output is high, the FF won't work. No, ma'am. Yeah, good question. See here, according to the block diagram of the register, the active clock pulse is negative. That is what I have shown here, negative trigger or the falling edge, right? So when the falling clock is having, I'll show you here, when the clock is having a falling edge, right? When the clock is having a falling edge, if you have the load value as 1, so this will be 1 and this will be negative, right? So here it is in terms of the clock signal, because whenever this is negative, this will be active. So clock will be given here. And when this is negative, if the load input is 1, then we'll get a negative clock here, and then this will get activated. So if it is 0 here, this negative clock will not be coming here, right? So it will not be coming at the output of the AND gate. So this will not be active. So for making the clock active and for the registers or the flip-flops to get that active clock pulse, the load input is very much required. So why we need load input is to activate the clock or hold the clock. To activate or deactivate the clock, we need this load input, right? So whenever load is 1, the clock is reaching to the flip-flop. If load is 0, the active clock will not reach the flip-flop. So that is why we need the gated clock, right? Ma'am, what is load input? Yes, ma'am, thank you. Okay. So this is given as load. The name of the input is given as load because it will make us understand better that if load is high, what do you mean by load? Load means whatever input we give here should get moved into the register. So that means if load is 1, whatever data we give here will be loaded into the register or moved into the register. So the name of the signal makes us clearly understand what is the operation taking place. Hence, this signal is named as load, right? So here, when load is 0, so you can see here, when load is 0, the register is not clocked. The clock signal will not reach the register and it holds its present value. But when load is 1, the clock signal is transmitted to the flip-flop clock inputs, right? When load is 1, that is what I showed you, right? This negative signal the negative clock signal will reach here and whatever data I have given here will get stored into the register. And the data applied at the D inputs will be loaded into the flip-flops on the falling edge of the clock. So this, if the diagram has without a bubble, then what will be the clock edge? If it was without a bubble here, if this bubble was not there, then what would be the type of clock? Rising edge. Very good. Yes, correct. So based on the symbol, you have to write this. If at all you write in the diagram, this is left to you whether you write a negative edge or a positive edge. You can write anything. If you write it as without bubble, then here you have to explain it as rising edge. If you write with bubble, then here you have to mention it as falling edge, right? Got the difference? Next, gating the clock. So wherever you want to store the previous content, you are using the gated clock. But when we gate the clock, there are certain timing problems. I think yesterday I explained you, right? The delay models, which are the two delay models we discussed yesterday? Can you answer? Which are the two delay models we discussed? But if we use gated clock, we will face many problems, ma'am. Yeah, that is what I'm telling you. Initial, it is not initial, Gunal. Inertial. Correct, you are correct, but you just make a change. It is not initial, it is inertial. I-N-E-R-T-I-A-L. It is inertial delay and ideal delay, right? Good. So these were the two delay models which we discussed yesterday. So when we use gated clocks, those problems may arise. So as a solution for that, we'll be using the registers or the flip-flops which are available with clock enable. So if flip-flops with clock enable are available, the register can be designed as shown in the next diagram. Right? So we'll move to the next slide. So this is the next slide. So here you can see the register which has clock enable. So this is your clock enable. C is nothing but clock enable. So this I think we had studied when we studied about the registers or the flip-flops. In the flip-flops, we had this one type which had the additional inputs. In the additional inputs, we saw this slide, right? After the delay models, then we saw this clock enable. So instead of having a gated clock, the load signal is directly connected to the clock enable. You can see that the load signal is connected to the clock enable pin. So when we do this, the clock is directly connected to the clock input, right? They are not gated. So, but whenever load is 1, even though the clock may be changing here, only then the flip-flop will be enabled for storing the data given at the data inputs. So only if load is 1, you can see that load is a active high signal. So whenever load is 1, only then the clock is enabled. What is this? C is clock enabled. So this will be allowed, whatever transitions are coming from the clock, that will be allowed inside the flip-flop only if this is 1. If this is 1, then what is the type of clock enable? It is negative trigger. So if the next negative trigger occurs, and if this is 1, only then this will be active. If this is 0, and even though a negative signal occurs, this will be inactive, right? Only when C is 1, if you get a negative edge, then the flip-flop will be active and whatever data is present here will be stored. Just a moment, I have to connect the battery charger. So here, I'll just erase this part. Yeah. So here, when C is 1 and when you get the next negative clock pulse, this flip-flop will be activated and whatever data is present at the input will be stored into the flip-flop, right? But here directly they are not connected through a gate. If we connect through a gate, because of the propagation delay, there will be a timing problem, right? Hence we use the flip-flops with clock enable. So this will be the solution for the timing delays when we use the load signal with gated clocks, right? So we'll move to the next one. Any doubts here? Okay. So next is register transfers. So that was for registers, and next is register transfers. So what do you mean by register transfers? So when you have to transfer data between one complete register to another register, or from data between 2 registers to 1 register. Whenever you want to transfer data from one register to another register, we call it as register transfers. So here, how to transfer data, transferring data between registers is a common operation in digital systems. The following diagram shows how data can be transferred from the output of one of the 2 registers. See how data can be transferred. Data can be transferred from the output of one of the 2 registers. From the output, see from this output, this is the register. From the output of this register, how it is getting transferred to the input of the other register into the 3rd register using a tri-state buffer. Do you all recollect what is tri-state buffer? What is Shrita? No. For what is this? Hashita ready? For what is it? No. I forgot what I asked at that time. Okay. So when the data has to be transferred from the output of one register to the input of the next register, we call it as register transfer, right? So when it can be transferred is mentioned here. So when enable is 1 and load is 1, but you have to observe the circuit here. See here, this is the enable signal and it is connected through a NOT gate. And before going to the operation, we'll just see what are the parts shown in this particular circuit, right? So which are the parts here? So this is register A1 and this is register A2, right? So this whole thing is, this is flip-flop A1 and this is flip-flop A2, and this both together it is register A. Similarly, here you have register B, which has 2 flip-flops, and here you have register Q, which has again 2 flip-flops. So the data has to move from either register A to register Q or from register B to register Q, right? Either this or this operation only can be performed. You cannot move the data of both these registers simultaneously to this Q register. Either the content of A will be moved to Q or the content of B can be moved to Q. So how is it done? So that we'll see now. How the data from either A or B can be moved into Q. Right? So here you have the enable signal which is connected at high. When enable is high, it is connected to register A. Please observe this. At high, it is connected to register A to the tri-state buffer. It is connected to the tri-state buffer, and the negative when the NOT gate is 0. When enable is 0, it is connected to the tri-state buffer of register B. Right? So when enable is 0, register B will be active, and when enable equals 1, register A will be active. Right? And here, this is tri-state buffer. So enable will be the, so yesterday we saw the tri-state buffers where this was the input and this was the activating signal, and this is C. So when B is high, the output is equal to A. When B equals high, output equal to A. When B equals 0, it was a open circuit in this. But here, because when B is 0, we have connected another register. Now it will be B. C equals B. Even that condition we are utilizing by connecting it to 0. Right? When it is open, we are connecting it to a different circuit. So that circuit will be connected here. Right? That register will be connected. So this is the operation of the enable. When enable is 1, register A will be active. When enable is 0, register B will be active. So that is done through the tri-state buffers. The activating of the registers is done through the tri-state buffers. Then here the details are given. When enable equals 1 and load equals 1. So where is the load signal? So this is the load signal. Here you have the load signal. Right? So enable should be 1 as well as load signal should be 1. So when both are 1, what happens? What will be the content of Q1? Can anyone tell what will be the content of Q1 and Q2? What will be the output at Q1 and Q2 when enable is 1 and load is 1? A1 and A2. Very good. Q1 will have, register A is also correct. So when load is, enable is 1 and load is 1, the contents of register A, right? The contents of register A will be moved into register Q. So A1 will be moved into Q1, that is this register, and A2 will be moved into Q2, right? So this is when enable is 1 and load is 1. But at the same time, if enable is 0, now assume that enable is 0. I give a 0 here. Now what happens? What is the output at Q1 and Q2? If enable is 0, what is the output at Q1 and Q2? Yeah, good. So when enable is 0, output will be B1 and B2 or the contents of B, correct? Correct. So the contents of register B will be stored in Q1 and Q2. So this is how the data from one register is stored into a other register. Understood? Okay, we'll move on to the next slide. I'll just clear this. So next is data transfer using a tri-state bus. Yeah. So now we have to know what is a bus. Data transfer using a tri-state bus. So can anyone tell what is the difference between a bus and a tri-state buffer? The difference between bus and a tri-state buffer. Will load be always 1? Yeah, if data has to be transferred, then it has to be always 1. If at all data transfer should not be done, then load can be made as 0. It depends on the user. If he wants all the data to be loaded continuously when the clock is active, then he can keep load as 1. If he doesn't want it always to be loaded by the next clock pulse, then he can change it to 0 and activate it whenever he requires it. Bus is a group of data wire, correct. Buffer stores, bus transfers. Buffer stores and bus transfer. This is also tri-state only. Both are tri-state only. Both have the same function, but it differs in the bits. Chitra. Yeah. Bus also stores. It is only a temporary storage. It is not a permanent storage. Buffer means it is temporary storage. It cannot store it for a long time. It will store the data until it is transferred. So only for the duration of transferring, it will store the data. Bus is used to connect flip-flops or devices. Yeah, it is connected, but the main thing is in a tri-state buffer, you have only one bit. Buffer is specified for single bit. But when it is for multiple bits, the same tri-state can be used as a bus. So when we have multiple bits to be operated, then we use a bus. So this is also register A, but the size of the bus is 8. So can you tell what is the number of bits in register A? See, the bus size is 8, and here we have register A. All the registers are mentioned with 8. So what does this 8 indicate with respect to register? What does the 8 indicate with respect to register? 8 bits, very good. So that means each register has 8 bits. So when I want to transfer 8 bits, I need a bus. So if you remember in your logic design lab, for the multiplexer, you used to define the input lines as 7 down to 0 and 2 down to 0. What did this represent? This also represented the bus. So whenever for a single variable you have multiple bits, then it is called as a bus, right? Then we represent it with a bus. So hence here the same operation what we saw previously, that was for bitwise we saw, but here we are seeing the for multiple bits. So the following figure shows how data can be transferred from one of the 4-bit registers into one of the 2 other registers. So these are 8-bit registers with tri-state outputs. So here you have register A, register B, register C, and register D. So the data containing in any one of these 4 registers, please listen, data of any one of these 4 registers can be moved into any one of these 2 registers. Suppose I want to move the data of B. So I can move it into either G, right? I can move it into G, or I can move it into register H. So this is OR. Both need not be done parallelly. Or if you want to load it, both also there is a option. So that we'll be seeing in the next slide, right? So for a bus, when we move multiple bits simultaneously from one register to another register, it can be done using a tri-state bus. So tri-state bus allows us to move multiple bits simultaneously from one register to other register, right? Okay, now we'll see how it is done. So here at the bottom, can you see a decoder? So this generates the enabled signals E and F. So if when E and F are 0, 0, when E and F are 0, 0, then register A will be active. Then contents of register A will be loaded into the bus. Then see, when A is active at 0, 0, so for this the enable signal is, I'll just write here, enable signal is 0, 0. For this enable signal is 0, 1. For this it is 1, 0, and for this it is 1, 1. So these are the enable signals, means the value of E and F, right? The first bit is E and the next bit is F. So when it is 0, 0, register A, the data from register A will be moving into the bus. It will be present in the bus only. It will not be moved into the directly into the register. So first operation is the data from the active register will be put into the bus. See, when the input is 0, 0. Now the input is 0, 0. That is the input to the decoder is 0, 0. So when it is 0, 0, the data from register A is stored into the bus only. So can you see here? It is now stored into the bus. It is loaded into the bus. Then if load G is 1, if this signal is 1, then from the bus it gets transferred into the register G. So for one operation, you need 2 signals to be active, right? If you want to transfer the data from register A to register G, then EF should be 0 and load G should be 1, right? Or if I want to transfer the data from register A to register H, it will be here. Suppose this is 0. If load G is 0 and load H is 1, can you guess what happens? If load G is 0 and load H is 1, can you guess what happens? Is multiplexer an example of bus map? Multiplexer is not an example, but multiplexer has multiple inputs, right? The inputs of the multiplexer are multiple. So that you can consider as a bus. Data is transferred to H. Data will be loaded to register H. Very good. So this is the correct answer. Data will be transferred to H from A. Good. So all of you have given correct answers. So when load G is 0 and load H is 1, so data from register A will already be present in the bus. So from the bus, it will get loaded into the register H. So understood, right? So next question. Suppose I'll just give the values of the signals. Tell me where the data is flowing from and to where it is flowing, right? At E, the input is 1, 0 and load G is 0, load H is 1. So now tell me from where to where the data is getting transferred. Observe the input of EF and observe the values of load G and load H and tell me from where to where it is moving. C to H, C to H. Yes, very good. C to bus, bus. This is very specific. Very good, Taman. So C to bus and bus to H. Yes. So this is the actual transfer. It is happening. So always the data first moves into the bus and then from the bus to the register. Directly it cannot move. So first the data is loaded into the bus. Then based on which load signal is high, it will be moved into that particular register. So all of you understood, right? How this is done? Okay. So then we'll move to the next one. So next is the same thing. Whatever I explained there, that is completely explained here. So I already told there. You can just go through the slide if you still have any doubts. What will happen when both the loads are 0? Very good. Ma'am, can there be a situation where the load for, yes, both are very good questions. I think in the slide it's already there. So if you can see here, if load equals G and load equals 1, I'll just go back to this. I'll just give the load values as 1 and 1, right? I'll give a different combination now. So here I'll give the input as 1 and this as 1. And here also load G is also 1, load H is also 1. So you already saw there. I don't know how many of you have read. So can you now tell from where to where the data is transferred? Just guess. Even if it is wrong, it's fine. Can you guess what happens? What is the data? Which data is moved from where to where? D to both G and H. Correct. Any other answers? D to bus, from bus to both registers. Very good. D to bus and from bus to both registers. Very good. So I think you all read it so fast. So when both the load signals are high, the data from the bus will get loaded into whatever data is present in the bus, that will get loaded into both the registers, right? If the register contents of, so what is the content of the register on the buses? Register D, because the enable signal is 1, 1. The content of register D is stored into the bus, and from the bus, the data is stored into both register G and register H, because both the signals are high, right? When suppose both signals are 0, this was one more question, right? When both are 0, the data just remains in the bus. It will not get transferred into either G or H. G and H still hold the previous data only. So when it is 0, when both are 0, the data will not move into any of the output registers. It will just stay on the bus itself. Right? Got your answer? Okay, so now we'll go for the next one. Any doubts in this? Tri-state buffer? Yes, good. So we'll move on to the next one. So this is the explanation. So now I'll hand over to Shalini ma'am for the topics on parallel adder with accumulator, right? So we'll just change over, just a moment. I'll stop the share. Yes, Naveen, for what you're telling, no, ma'am. No doubts, huh? And Aditi, 1 second, I'll just open the slide. Okay. Aditi, if E is 0 and F is 0, won't the output be 1? Output, what output you're telling? Whatever data we give, if we give 1 at A, like it is not 1 bit, right? It is from the register. Register A will be active. If E and F is 0, then register A will be active. Whatever data is present in register A, that will be get stored into the bus, and from the bus it will either get loaded into the G register or H register, depending whichever is high. Aditi, got your answer? Because it is not a single bit, the output can't be 1. And output is there at 2-3 stages. Aditi, did you listen? Ma'am, but there is a bubble at the encoder. Yes, bubble, not the encoder. It is not at all the encoder, first of all. What was that? One second, I'll just share my screen so that you can. Just a moment. ಇದೆ ಇದೆ. So decoder has bubbles. Also at the input of the registers also, the enable signals also have the bubbles. So if you observe that, if the output of the decoder is 1, then again at the input of the register 8 becomes 0. Good observation. So because you have bubbles at both the places, it will get again it will come back to the same value as we give at the decimal of the value we give at the E and F. Got it? Did you understand, Aditi? Chandrakir, as soon as we change the input in decoder, will the data in bus get cleared? It will not get cleared. Whatever register is active, the data of that register will be moved into the bus. The data in the bus, it will not get cleared unless we have some clear signal. But here we don't have any clear signal. So whichever register is active at that instant, the data of that register gets loaded into the bus. And that was the question of Chandra Kiran. And what else? Decoder. Yeah, it is decoder. Correct. So it was not an encoder, it was a decoder. So it is a good observation again. At the decoder also you have bubbles, but at the same time, at the enable signals also you have the bubble. So if it is a 0 here, at the input of the registers, register 8 becomes 1. Right? So is it clear? Your doubts, and there was some more questions. Siddharth, we can do it without bubble at the decoder, ma'am. You can do it, but it depends on the application. So why that bubble is used? Because that decoder, the IC whichever they have used, maybe that IC is having an active low signal, hence the bubble is there, right? So if you want it to be 1 here, again you have to use a active low enable signal. So it all depends on which IC of the decoder you are using it. Ma'am, so enable is active low. Yeah, enable is also active low. Output of decoder is also active low, and all the enable signals are also active low. Okay. Nishan, the bus has data like data in a stack? No, ma'am. Stack is different. Bus is a parallel memory. So all the 8 bits will be stored parallelly in the bus. But stack, it has a particular direction. In a stack, the data is stored in a particular direction. Whereas bus, it has all the 8 bits in parallel. So the data can be stored parallelly. It is like parallel in parallel out register. Whereas stack has a single mode of operation. Entry and exit both from only one single direction. First in, first. No. In stack it is first in, last out, or last in, first out. Naveen, stack is not first in, first out. Q is first in, first out. Q is first in, first out, whereas stack is last in, first out. So last, I think the best example will be a CD stack, where in the middle you'll have a rod-like thing. We'll be loading the CDs, and whatever CD you put at the top, only that can be taken out first. You don't have any other way to take out the CD. Got it? First in, first out is Q, and stack is last in, first out, LIFO. Okay. Any other doubts? Okay, so over to Shalini ma'am.
Good morning, everyone. Um, Today we are discussing Module 5, registers and counters. Many students think that Module 5 is tough. Why do we need to study that for exams? We can leave Module 5 anyways. We are okay with Module 1 to 4. Many students think like that and they easily leave off Module 5. But my sincere request is please don't leave module 5. Module 5 is easy to score. The questions that they occur, they are easy to score. And if you are expecting some theory kind of question in the complete logic design, in module 5, you can expect some theory kind of questions. And you have design of counters, right? Those design of counters, they are required for your lab sessions also. And design of counters are easy to understand and easy to solve if you have the knowledge of flip-flops. And you can score well also because the design of counters question, it occurs for 12 to 15 marks. Okay, so please don't leave module 5. It is not tough, it is easy. And you can expect some theory questions in that. Okay, so just now ma'am told you about registers. So what are registers? Registers are group of flip-flops. It can be any type of flip-flop. It can be D flip-flop, RS flip-flop, JK flip-flop, T flip-flop, any flip-flop joined together, any type of flip-flops joined together, they form registers. So we flip-flop were able to store 1 bit of information, 1 bit of data, right? So, but we want sequence of information, sequence of bits to be stored or sequence of bits to be transferred, right? Then we go to the concept called registers. So in registers, since we are cascading different types, different types of flip-flops together, you can store bits in the flip-flops and more than 1 bit, right? Because they're cascaded. So you can store information. As a whole, I can say you can store the information in registers in the form of bits. So let us see here. Coming to this, the next slide. Just a second. Okay. So coming to this, we are studying parallel adders with accumulators. So till now we were studying how 1 bit was stored and 1 bit was processed, 1 bit was transferred, right? We studied that till now. But we were not studying how group of bits processed, group of bits introduced into register, group of bits transferred out of register, right? We are studying how the bits could be transferred to a register in groups. Okay, in groups, how it can be sent, how they can be processed, and how we can get the output, right? So for that, we are starting with a simple example, that is parallel adders with accumulators. We are going to see how we can send bits to the adders and perform the addition operation and get the result, right? So we use different types of registers for different purposes. Can you name some registers? Can you name some registers? You have studied this in your theory classes. Can you name some registers? Parallel in, parallel out. Okay, okay. Have you heard about accumulator register? Accumulator register? Accumulator? Yes, in CO. What is the job of accumulator? What does it do? What does it do? It stores the processed results, arithmetic results, right? It is used to store the computed value. It is used to store the results which you have got, right? So for that purpose, we are using accumulators. So here you can see in the diagram, you have flip-flops and you have adders. Okay, so we are using flip-flops with adders. Okay, and here these flip-flops put together, they form accumulator register. They work as accumulator register. So which flip-flop we have used here? We have used D flip-flop. What is the importance of D flip-flop? Can you tell me the importance of D flip-flop? Or you can tell me the characteristic of D flip-flop. What's the important characteristic? When we want to add two numbers, we move one number to the accumulator. Okay, the output is same as the input. Correct. Naveen, it is correct. In D flip-flop, whatever input you give, the same comes as output. Input equal to output is correct, Harshika. Good. That is the main characteristic of D flip-flop. Whatever you give as input, that comes out as output. Correct. So using that characteristic of D flip-flop, we are cascading these D flip-flops together to form a accumulator register. Okay, and then we are using adders here. You have come across adder circuit in your labs, right? Which gates you have used to get the adder circuit? You have done the experiment in the lab. Which are the basic gates you use to get the adder circuits? Yes, yes, yes. I hope you have seen the outputs using full adder, half adder, right? So here we have full adder. Okay, full adder connected to D flip-flop. And what are the additional inputs we are giving here? Clear input. Why do you need to clear the input over here? What is the purpose? Yesterday I told you, clear input, there are additional inputs, right? Clear input, it flushes the register. Yeah, you need to keep on flushing the register every time when you want to store a new result, right? So for that purpose, we are using clear N. Okay, and then clock input is also given, right? Clock input is very important for the flip-flops to work, right? And we will see what is the job of add signal. Add signal, the name itself tells, it helps to add the values when it is high. Okay, since it has theory part to be explained, I cannot put everything over here. So I have the PDF document where I have highlighted the important things which you have to present in your answers. I'll show you that. Okay. Okay. So this is parallel adder with accumulator. Is it visible? Yes. So in computer circuits, it is frequently desirable to store one number in a register of flip-flops called accumulator, right? You want to store some result, we are using accumulator register and add a second number to it. Suppose you take one second, I'm using this one now. Suppose you take X has one number. I can consider this X is made up of bits X0, X1, X2 up to Xn minus 1. And Y has another data which is made up of Y0, Y1, Y2 up to Yn minus 1, right? I want to add these two. So how you can add these two, we will see in this accumulator working. Okay. So one way to build a parallel adder with accumulator, that you already know that we are using accumulator to the register to add to the adder. Okay. And here you can see the circuit diagram. Suppose that X, as I told, I have written in the reverse order, X is equal to Xn, X2, X1. It is stored in accumulator, which is stored in accumulator X. It's already there in accumulator. Then the number Y is equal to Yn, Y2, Y1 is applied to the full adder. So where are you giving the inputs? You are giving the inputs like this. So Y1, so here you are giving the inputs through Y1, Y2, like this, Y3, Y4, Yi, Yn. Okay. And then, and after the carry has propagated through the adders, the sum of X and Y appears at the adder outputs. So where do we get the sum? Here we are getting the sum. In the adder outputs, we are getting the sum, right? An add signal, AD signal is used to load the adder outputs into the accumulator. So whatever you have got here, S1, S2, Si, Sn, right? If you make add signal high, this will be loaded to the accumulator. Okay, I hope up to here it is clear. If Si is 1, so what should be X1? Since we are using D flip-flop, what should be X1? Yes, correct, exactly. If Si is 0, what should be X1? It should be 0 because we are using D flip-flop, right? So whatever we give has the output here that is fed into the D flip-flop and that is coming out, it is again giving to the full adder. Okay, so this is how it is made to work, and the carry is propagated from one full adder output to another full adder, this to next, and it continues. Okay, then I highlighted all these things because in exam they expect these concepts from you. Because it's a theoretical question, I wanted to stress the important points which you have to show in your answers. Okay. Okay. So observe that the adder with the accumulator is iterative, because once you get the sum here, it will be what? Coming back, right? So it is again sent to the adder. So each cell contains the full adder and associated with the accumulator flip-flop. This, one second. You can consider the whole thing here as one cell. This has one cell. Okay, so one cell consists of a full adder and a flip-flop. Okay. So up to here it is clear. So before addition can take place, the accumulator must be loaded with X. So this can be accomplished in several ways. So before that, what we have to do, we have to clear everything in the accumulator register. The easiest way is to first clear the accumulator using synchronous clear inputs. That is what we are using there. We are using clear inputs for clearing it. Then alternatively, we could select either Y input or the adder output to load into the accumulator. So this, the whole concept, this one cell, which consists of a flip-flop and a full adder, this whole concept can be shown with the help of a multiplexer like this. So can you tell me actually what is happening now? I have introduced a multiplexer here. So it is that we need not clear the accumulator register every time. Okay. So what does it do? What is the job of a multiplexer here? Can anyone tell me? What is the job of a multiplexer? Can't we use other flip-flops, ma'am? Okay. Now I want you to answer, why are we using the multiplexer here? The same cell, it is represented with the multiplexer to select the inputs. Very good. So which are the inputs we are going to select? Which are the inputs here? Output of the multiplexer is given to D flip-flop. Okay, then see here, you can give Yi and you can give Si. Okay, so that is given to the multiplexer. It's either 0, 0, 0, 1, 1, 0, 1, 1 combination. Correct. The sum and Y. Correct. Kunal, it is correct. Tamanna, it is correct. So based on different combinations, either you can send Yi or you can send sum. Then again, whatever you are going to get, whether you have sent Yi or if you have sent Si, it will be coming back to the full adder. So here you are taking the different combinations. Let me show you. So here you can observe that the following figure shows the typical cell of adder with accumulator flip-flop loaded directly from Yi. So when LD is 1, the multiplexer selects Yi. And Yi is loaded into the accumulator flip-flop Xi. On the rising edge of the clock pulse, we are taking the rising edge of the clock pulse. When AD equal to 1 and load equals 0, the adder output is loaded into Xi. Okay, that's what one of you answered. We are going to take different combinations of input and we take selectively whatever we want to the accumulator. We want SI to the accumulator, or we want YI to the accumulator. We are going to selectively take based on the combinations given to AD and load. Okay. So the AD and load signals are all together to enable the clock when either addition or loading occurs. So you should enable the clock because we are transferring the data, transferring the bit in the rising edge of the clock pulse. That is why. So when AD equal to LD equal to 0, the clock is disabled and the accumulator outputs do not change. Obviously, when add signal is 0 and we are not loading anything, then the clock is disabled, right? So because we are using OR gate here, if both are zeros, the output is 0, the clock is disabled and the accumulator outputs do not change. Okay, so this is how you need to write the answer. It's a theoretical question. Parallel adder with accumulator. You have to write this diagram. I hope you have understood. You are sending the data in the form of Y1, Y2, Yi, Yn, okay, to the full adder, and Y bits are given here. To take X bits, we are taking it from accumulator and you are adding it, and finally you are going to get sum. This sum is stored in accumulator register. Okay. Suppose you want that sum again, it is again sent to full adder. So it becomes an iterative process. Okay. Suppose you don't want it, you are going to use the clear. Okay. So instead of making the cell work like this, instead of clearing the register every time, we are making use of a multiplexer here. The one cell is replaced like this. You can replace all the cells here in the similar way. Okay. So all these things you need to write, and they can ask you this question for 6 marks, 5 to 6 marks. So you have to be fast in writing the diagram. See, once you are familiar with the flip-flops, connections, why do we give clock input, clear input, adders, how are we connecting adders, how are we taking the carry out, how are we giving the inputs. If you are familiar with the process, you can write the diagrams very fast. It is easy, right? You can write it now. Okay, shall I go to the next concept? Okay. So now coming to, yes, ma'am. Okay. So that's why I'm telling you, don't leave module 5 thinking that it is at the end of all the modules and it is tough. It's not tough. Okay. Now coming to the next concept, shift registers. Since you have already studied in your class, how many types of registers are there? How many types of registers are there? Can you please tell me? Four. Which are those? Good, good. 4. Yeah. Which are those? They are, yes, SISO, SIPO, PIPO, PISO. Yes, you already know this. SISO is serial in, serial out, serial in, parallel out, then parallel in, serial out, then parallel in, parallel out. So these are the different types of shift registers that are available, and we can use them to shift the data accordingly, according to the requirement. Okay. So how can you define a shift register? How can you define a shift register? What is shift register? The name itself tells you can store something and you can shift something. Something in the sense data. You can store some data, you can shift data, right? So that is why they are called shift registers. You can store and you can shift. So for that, a shift register is clearly defined here like this. A shift register is a register in which binary data can be stored. And this data can be shifted to the left or right when a shift signal is applied. Okay. So this is the more apt definition for a shift register. A shift register is a register in which binary data can be stored, and this data can be shifted to the left or to right when shift signal is applied. And bits shifted out one end of the register may be lost. It is according to how you design the register, right? The bits coming out of the register may be lost, or you can use a feedback circuit where the data comes back again to the first flip-flop, right? The data comes again to the first flip-flop. Okay, so there are two ways to shift data into a register. So that is, they have again given it serial or parallel, how you can shift the data into the register. If you consider this as a register, so if you consider, one second. If you consider this as a register, okay, so you can shift the data serially like this, or you can shift the data parallelly in. You can shift like this, input. This is also input. And we can take parallelly out like this, right? You can take parallelly out. So this is how you can send data into the register and take out the data from the register. Okay. Now you can see this diagram. Just have a glance to it. You already know all these things. So which is MSB and which is LSB, it matters a lot when you're shifting the bits. You have to concentrate on MSB bit and LSB bit, which bit you're pushing in. It matters a lot. Okay. So here they have used 8-bit register, serial data input, serial data output. So serial in, serial out, serial in, parallel out, parallel in, serial out, parallel in, parallel out. Okay, types of shift registers. So here we have a register, flip-flop connections are done. Again, here we are using D flip-flop. Suppose I want to shift 4 bits of information. 4 bits of information. How many flip-flops do I need? Suppose I need to shift 8 bits of information. How many flip-flops do I need? 8 flip-flops. Very good. So it all depends on the number of bits I want to shift. So I can say this has a 4-bit shift register, a 4-bit right shift register. Okay. So why? Because the data is moving in this direction. The data is moving in the right direction. Then which are the other inputs we have given here? Which are the other inputs? Shift and clock. What is the need for shift input? What happens when shift is high? When shift is high, the bit starts shifting from one flip-flop to another flip-flop. Okay, and obviously the clock input is high. We are taking the positive edge for considering the shifting of bits. Positive edge triggered. Okay, so SI means it is serial in, serial out. And here we have taken a feedback circuit so that the output which comes out from the last flip-flop is not lost. That output which is coming out of the last flip-flop is sent as the input to the first flip-flop. Right? Okay. So we'll see. So in the figure, we can see a 4-bit shift register with serial input and output constructed from D flip-flops. When shift is 1, the clock is enabled and the shifting occurs on the rising edge of the clock. So when shift is 0, no shifting occurs. And the data in the register is unchanged. I have taken this from your prescribed textbook only. Okay. At the same time, the output of the first flip-flop is loaded into the second flip-flop. You know that. So there will be delay in the registers because the second flip-flop waits for the input from the first flip-flop, right? And the third flip-flop waits from the output from the what? From the second flip-flop. So like that. Each flip-flop which is ahead waits the output coming from the previous flip-flop, right? The serial input SI is loaded into the first flip-flop. This is the first flip-flop, Q3, by rising edge of the clock. At the same time, the output of the first flip-flop is loaded into the second flip-flop. Suppose you are loading a 0 here or 1 here, say 1 here. So it is processed. Since it's a D flip-flop, the output coming here is 1 only, obviously. So this will be sent to the second flip-flop. Okay. So the output of the second flip-flop is loaded into the third flip-flop, and the output of the third flip-flop is loaded into the last flip-flop. It continues like that. So because of the propagation delay of the flip-flops, you know, I told you just now why the delay occurs. By the time the last flip-flop receives the information, it would be in like T1, T2, T3, T4, fourth cycle. Okay. The first flip-flop receives in first cycle itself, right? So the output value loaded into each flip-flop is the value before the rising clock edge. Okay. So these are easy answers. If you understand the working of register well, you can easily present this answer. Okay. So here they have given an example. Illustrate the timing when shift register initially contains 0, 1, 0, 1, and the serial input sequence is 1, 1, 0, 1. So how are you going to show this? How are you going to show this? The clock input we are taking first, and the next one is serial input. This is the serial input data. It is the serial input data, and you can see how the bits are shifting in this timing diagram. How are they shifting? So what is the initial data? Initial bits. It is the initial bit is to say 0, 1, 0, 1. Initial bit is 0, 1, 0, 1. Then what happens? What are we giving now? This is the input. So how are you going to give the input? 1, 1, 0, 1. MSB. This is MSB and this is LSB. Okay. So what happens first when you push the first bit? So this comes here, right? So what will happen? It will be this comes here, right? So it will be, since it comes here, it will be 1, 1, 0, 1, 0, 1, 0, right? And then next when it comes, it will be 1, 1, 0, 1. And then when it comes next, it is 0, 1, 1, 0, right? And then when it comes next, what happens? 1, 0, 1, 1. The shifting occurs. So I can say this has Q3 and this has Q2 and this has Q1 and this has Q0. Q3, Q2, Q1, Q0. So accordingly, you need to draw the timing diagram. So here you can see the SI is shifting the data. So what is the data we are shifting? 1, 1, 0, 1. So see here, you can see it is 1, 1, 0, 1. Can you see this? It is 1, 1, 0, 1. Then Q3, you just see the Q3 column, and according to that, you have to write the waveform. You can see here Q3 column. Initially it is 0, 0, 1, 1, 0, 1, 1, 0, right? And see the Q2 column. What is Q2 column? 1, 0, right? 1, 1, 0. Then see the Q1 column. It is 0, 1, 0, 1, 1. Then Q0, it is 1, 0, 1, 0, 1. That is how you need to write the timing diagram. So they just shift. It comes here, this comes here, the new bit sets in. So this is how you need to write the timing diagram for a 4-bit register. Can you explain once more this? Explain it once again. Okay. Okay, I'll explain. See, initially we have the data. The register already contains this. Okay, that is 0, 1, 0, 1. It already has. What is the new sequence you need to push into the register? The new sequence is 1, 1, 0, 1. So in this, which is LSB? This is LSB and this is MSB. Right. So initially we have this. Now we need to push the data in this form. I am writing like this. Okay. It is 1, 1, 0, 1. Suppose I push this. What happens? This will come here. So it will come here. This will come here. So it comes here. So this will come to this position. So it will be 0 and this will come here. So this will become 1. Suppose I take this as Q3, Q2, Q1, Q0. Okay. Then suppose you want to push the next bit. What happens? This will come here and this will come here and this will come here, and the new bit, this is the new thing what you want to put, it comes here. Getting? Then I want to push this bit. So how am I pushing that? So this comes here, this comes here, the 0. The 0 comes here and this 1 comes here and this 1 comes here and this 0 is pushed. The next, you have to push 1. What happens? This 1 comes here and this 1 comes here, this 0 comes here and this one. So finally, you will get this. Whatever you have pushed in, you are going to get this at the end of this flip-flop. Got it? Or any doubts in this? Ma'am, explain it. Mahima, you understood? Rahul got it? Mahima? Okay. Naveen's doubt is, ma'am, is it wrong if we don't show delay in timing diagram? Answer. Ma'am, is it wrong if we don't show the delay in timing diagram? Is it wrong or right? You only tell me. You tell me. What do you feel? You have to show it or not? It's wrong. You need to show the delay. Is the delay shown in this timing diagram? Is it shown? What? Is it shown in the current diagram which is given in your book? Yes, yes. Correct. It is shown. Right? So you can see correctly at the rising edge only, you cannot see the change or the data moving. You can see after some time, right? You can see this. You can see. suddenly it is not falling, right? No, it's not wrong. It's optional. Better to show some delay. Few milliseconds delay, it will be fine. In some books, I have observed they have not shown exactly at the rising edge, exactly at the falling edge, if they are considering the bubbled clock. Exactly there only they have shown. But little delay showing is correct procedure. It's nothing wrong. Okay, they have given like directly in the rising edge, the data is going there at the same time. In the falling edge, if you have used the bubbled clock, it is coming out. No, it is not correct. You have to show little delay. Little delay is fine. Yeah, obviously delay occurs because we are cascading the flip-flops and finally at the end we are getting the output, right? Okay. Yeah. Any other doubts? See, even this is a simple question, right? You can easily answer this. And they have asked this question. The question is, you have to design a right shift register using D flip-flops and show an example. So what example you can show? This example you can show, right? Or else sometimes what they have done is they have only given the data, initial data and the new sequence. You can do it, right? You can show this in the form of truth table. You can keep this as Q3, Q2, Q1, Q0. You can easily show it in the form of truth table and you can easily show it in the form of timing diagram also, right? Suppose if they don't mention the initial data, here they have given the initial data as 0101, 0101. And sometimes they don't mention this, simply they give this the sequence which you need to input. Okay, so then what you should do, you should take the initial data as 000. Take it as 0. Then you start giving this input. Got it? Any doubts in this question? It's an important question. Suppose I ask you to design a flip-flop, a register using 6 flip-flops. You can do it now, right? It is not a problem now. Yeah. You can work with any number of flip-flops. It all depends on how the data we are shifting, in what way we are taking, whether we are taking it from MSB or LSB. In your book, they have considered this. Okay, Nishant. Like how we concentrate on MSB in writing K-maps. Changing MSB changes the way we write the K-maps numbering, right? So that is how. Okay. So next we shall go to the concept, other concept. I'll just erase this. But better mention which bit you are sending first, MSB or LSB. In your answers, you mention MSB, LSB, which bit you are shifting. Now we are seeing 8-bit serial in, serial out shift register. So it's a 8-bit serial in, serial out shift register, serial in, serial out, and clock. So since it's a 8-bit serial in, serial out shift register, we are using 8 flip-flops, and here we are using SR flip-flop. SR flip-flop, and clock input is given. So this is just one more example they have given. There we saw 4-bit shift register. Here we are seeing 8-bit shift register. Suppose you are giving a input in the second clock pulse. In the second clock pulse, you are giving this here. So how many registers are there? How many flip-flops are there? 1, 2, 3, 4, 5, 6, 7, 8, right? So there are 8 flip-flops. So what you can observe here in this is, suppose you are giving the input in the second pulse in between this. So what happens is you are going to get the result after 7 clock periods, because it need to pass through these 7 flip-flops, 1, 2, 3, 4, 5, 6, 7 flip-flops. And after 7 clock periods, you are going to get this result. Whatever the input you have given here, it is coming here. Output occurs after 7 clock periods. Suppose you are giving the input here, the output is occurring in the 12th, that is after 11th. This is just an example to show when the data occurs outside at the output, when you give the data input once. After how many clock periods it comes out. Of course, some delay is introduced. This is just an example to show that you will not immediately get the output. Those who have worked with the trainer kit, you might have observed that you need to, if you are using the manual clock, you need to keep on pressing the clock, right? Then the bits keep on shifting, right? So that is how it works. So coming to the next one, here it is a 4-bit parallel in, parallel out shift register. So the name itself tells it's a 4-bit parallel in. You are giving D0, D1, D2, D3 as input and Q0, Q1, Q2, Q3 as output. Okay. So serial in, shift enable, load enable, clock. Okay. So here you can see this parallel in, parallel out right shift register is constructed with the help of multiplexers. It is parallel in, parallel out, and serial in is also there because we are shifting right. Okay. And load, you know already, to load the data. Clock, we are considering the positive edge trigger or negative edge trigger. Here we are considering the negative edge trigger, and we are getting the output SO. SO is the output, serial output. So here you can see the construction of the parallel in, parallel out right shift register. So for that, we have multiplexer attached to the flip-flops. Again, we are using D flip-flop. We are using D flip-flop. And can you tell me the outputs here? Which are the outputs here? Q0, Q1, Q2, Q3 are the outputs, and the inputs, which are the inputs? How are you going to give the inputs? Why are we using multiplexer here? Why are we using the multiplexer? SH, if it is high, if SH is high, then what happens? The data gets shifted. If SH is low, then the data is not shifted. If load is high, then you are loading the data to the flip-flop. If load is 0, we are not loading the data to the flip-flop, right? S in is serial in. Any doubts? So here we are taking the different combinations. I'll let you know. If you want, you can note down. Here we are taking SH, that is equal to L equal to 0. So if SH is equal to L equal to 0, then what happens? What happens? SH is 0, L is 0. Then you consider this part. We are putting the data inside through this. So consider this cell first. You can say it as cell. Yeah, consider this cell first. If SH is equal to L is equal to 0, what happens? what happens? The flip-flop Q3 output is selected. The flip-flop Q3 output flip-flop Q3 output is selected, okay, by the mux. Mux selects Q3 output. Suppose SH is equal to 0 and L equal to 1. The data input, just see, SH 0 and data, L 1. If it is 1, 0, 1 combination. If it is 0, 1 combination, see here. If it is 0, 1 combination, we are giving the data through D3. If it is 0, 0 combination, which is selected, Q3 is selected. That is, then if SH is equal to 1, okay, and L is equal to 0 or 1, L equal to 0 or 1, then which is selected? Serial input is selected. So that is why we are using multiplexer. The multiplexer placed here makes our job easy to select either Q3 or D3 or SI. Because we have so many input output here, right? We have to deal with Q3, we have to deal with D3, we have to deal with SI. So we can deal with all this Q3, D3, SI with the help of multiplexer. Okay. So then each cell is constructed like that. So Q3, Q2, Q1, Q0. Then coming down, you can see the shift register operation. You can see here, if shift is 0, load is 0. The next state, Q3 plus, Q2 plus, Q1 plus, Q0 plus, they remain same. There is no change. Q3, Q2, Q1, Q0. Because you are not shifting, you are not loading anything. Next, when shift is 0 and load is 1, when shift is 0, load is 1, we are loading the data D3, D2, D1, D0 to, that is what we are seeing Q0, Q1, Q2, Q3 as output. Right, we are loading. So where are we loading? From here we are loading D3, D2, D1, D0. So obviously the Q3, Q2, Q1, Q0 will contain the value present in D3, D2, D1, D0. That is load. Got it? Then when shift is 1 and load is don't care. When shift is 1 and load is don't care, that means what? You are shifting some data. When you shift some data, here, what does Q3 will contain? The new shifted data, right? So that is SI. Q2 will contain what? Whatever that is there in Q3, right? And Q1 will contain what? Whatever that is there in Q2. Q2 previously had what? D2, right? And then Q1 will contain what? Q1 will contain, sorry, Q0 will contain whatever that was there in the previous Q1, shifting, right? So like this, the shifting happens. If you want, I'll tell you once again. The last combination, suppose shift is 1 and load is don't care, okay? Then what happens? You are going to shift the data. Load can be anything. It can be high or low. Once you are shifting the data, the Q3 will contain shifted data, whatever the new data that you are shifting. Then this Q2 will contain Q3. What was there in Q3 before? D3, right? The data is that one. Then Q2 will be present in Q1 and Q0 contains Q1. Next state, I'm talking about the next state. So that is how the right shift occurs. FF is like in the disabled mode, to shift occurs, but the output is transferred back to S1. How, ma'am? I'll let you know. See, I'll erase this. 1 second. You are okay with these two combinations. The last combination I'm telling you now, it is high. Shift is high. When shift is high, you are shifting the data into the register, right? So once you shift the data, where does it come? Once you shift the data, where does it come? It comes to the first flip-flop through the multiplexer, right? Then you can observe here, we have Q3, Q2, Q1, Q0. Here you can observe it is Q3, Q2, Q1, Q0, right? When you are shifting one here, what happens? SI is the name given. So that SI is written here. So the Q3, it is D flip-flop, right? Whatever you give here, that will be reflected in Q3, right? So SI will be present in the next state, Q3 plus. Then shifting occurs. What does Q2 contain? What does Q2 contain now? This data, whatever that is there in Q3. What does Q1 contain? Whatever that is there in Q2. What does Q1 contain? Right, sorry, what does Q0 contain? The last one. It contains whatever that is there in Q1. When you shift the data, the first output, the Q3 will contain SI. Then Q2 will contain Q3. It is shifted. Then Q1, this one, Q1 will contain what? Q2, the data that is present in Q2. Then what does Q0 contain? The next state, the data that is present in Q1. That is how the right shift happens. Any doubts? Understood, Manoj? Manoj got it? Okay. Shall I move ahead? So this is parallel in, parallel out, right shift, register. So if you write the answer for this in a proper way, you can fetch full marks. Isn't it easy to write? Is there any thing that is very difficult to understand or difficult to present your answer? Nothing like that. It is a easy one, but the people who have not seen the flip-flops, registers, circuit diagrams in the beginning, if they just see this circuit, they feel it scary, like how tough it is and all. It's not so tough. Can you explain when inputs are 0, 0? When the inputs are 0, 0, Artik, what happens? Since we are not loading anything, the data remains same. Q3, Q2, Q1, Q0, they contain the same data since we are not loading anything. We are not loading, we are not shifting. 0 means what? We are not doing anything. So when we are not doing anything, Q3, Q2, Q1, Q0 retains the previous data that is present in the flip-flops. So there is no change. It is a no change state. So when we load something, that is when we give 0, 1, when we give 0, 1, that means 1 means what? This load is become high. When L becomes 1, then we are loading. How we are loading? D3, D2, D1, D0 we are loading, right? We are loading the data, that is load. I hope you are clear with the concept. Artik, got it? Okay. Okay. I'll move on to the next concept. See, these are all easy things. Please don't leave. All these are easy concepts. You can explain the same thing in your way of presenting the answers. Okay, you can express it. So then coming to here, they have given Q3 plus, Q2 plus, Q1 plus, Q0 plus. So based on this, they have given the equation. So just see Q3, Q2, Q1, Q0. So SH dash. Yeah, now just see, observe here how you got that equation. So this is SH dash Q3 plus. For first Q3 plus you are getting, how are you getting? SH dash, right? Because we are getting the SOP expression. SH dash, then L dash Q3. Okay, then what is this? SH bar L D3. SH bar L D3. Right? Then SH SI, because it is don't care, we are not considering it. It is SH SI. So that is how we are going to get Q3, the next state. Can you get the equation for Q2 plus? Can you tell me the equation for Q2 plus? Please tell me the equation for Q2 plus. Yeah, what should be the equation for Q2 plus? Shall I repeat once again? Yes, for Q2 plus it is SH dash. Okay, I'll let you know. Similarly, get it for Q1 plus. So for Q2 plus it is SH dash. This one, first one, SH dash, then L dash. L dash you should get, Harshita. SH dash, L dash, Q2, right? You have to start from the first. SH dash, L dash, Q2. Okay. Okay, I'll repeat it. So how are you going to get the equation for Q3 plus? Here for Q3 plus, just observe this table. In the table, to get Q3 plus, SH dash we consider, then L dash we consider, and Q3, right? SH dash, L dash, Q3. Then plus, what's the next thing? SH dash, you are going to get the equation for this whole column first. SH dash, L, because 1 is there, L and D3. Then SH, then SI. Since there is a don't care, we are not considering the don't care, we are writing this. Okay. Similarly, we shall write it for Q2 plus. For Q2 plus, how are you going to get? Just concentrate on this column now. It is SH dash, right? L dash Q2 plus SH dash L D2 plus SH, then Q3. Got it? Now get the equation for the next state of Q1 plus. How are you going to get? Q1, and similarly get for Q0. Similarly get for Q0. Yes, Q1, it is SH dash L dash Q1. Okay. Yeah, Preeti is correct. And what is the answer for Q0 next state? It is, yeah, even Harshita is correct. Obtain the equation for Q0 next state. Gunal, this is for which state you are getting, Gunal? You have to mention in the LHS of the expression. Q0. Okay, correct. So this is how you need to get. I hope all of you understood this concept. So this is a 4-bit parallel in, parallel out shift register. They have asked this question in the previous exams. So you need to write this diagram. I hope it is easy for you now to write this diagram. It doesn't take much time. You need to write the truth table and you need to write the expression. And finally, you need to write the timing diagram. Taking an example. They have taken one, some random example they have taken and they have written the timing diagram. Just observe the timing diagram. So in the, that is Q3, Q2, Q1 and Q0. So this is D3, D1, D0. It is nothing but whatever the inputs given here. D3, D2, D1, D0. Okay. So some random input they have given. So if you are giving the data like this, so here D2 is missing. D2 has to be put here. Okay. Then you have to show the data, how it propagates. So Q3, it is going like this. Then in the Q2, it propagates, it shifts, right? Then you are giving some data again, and it is shifting like this. Okay. Then again in Q0, it is shifting like this. You take some random data, like how you took like 1, 1, 0, 1, right? You took like this 1, 1, 1, 1, 0, 1. Take that and you can show the shifting. Shifting diagram, timing diagram is same for all the shifting right shift registers. It is shifting like this. So you have to mention the T0, T1, T2, T3, T4, T5. You can take your own example and you can show the shifting. That's what, Manoj, you can take any value to write the timing diagram. Your own values you can take. If they ask you to explain with an example, you can take 1101 as I showed you before. Here they have taken, yeah, here also they have taken 1101. Okay, so you can show the shifting. You can take your own example and mention which is the MSB and LSB, how the data is shifting. That is what, see here, 0, 1, 1, 0 only they have taken. It is there in your textbook. I'm teaching from your textbook only. Okay, you can take any example. In your book, everywhere they have taken this as example, 1101. Shift, that is, the shift is 1101. Load is, see here, initially you will load. So that is why it is 1. Then it is 0. Initially only you will load. Load will be high initially. Then you need not keep on loading because the data moves from one flip-flop to another flip-flop. You don't need to load it from external agent. So initially load will be high, then it will be low. Got it? Shift is whatever you take, like 0, 1, 1, 0. This is what they have taken. 0, 1, 1, 0. This data. Shift, you have to shift this. And with some delay, they have shown the timing diagrams. So I hope you are clear with this concept. You can take any 4-bit information and you can process it. Okay. And remember, the example bits you take should match with the type of register you are using, how many bit register you are using. Suppose you are taking a 5-bit example and you are writing 4 flip-flops. It shows your answer is wrong, right? What about D? D here, it is not required. We are mainly concentrating on C. We mainly concentrate here on clock and we concentrate here on load. Load initially it will be 1 and later it becomes 0. Then shift is the data which we are going to shift. Then D0, D1, D2, D3 is the bits which you consider and the bits keep shifting. That is D. Timing diagram, you can take any bit, that is 4-bit value, and you can show the shifting as you shown in the previous diagram. Both are same. They are similar. This is how, this I explained, right? This diagram I explained, right? The same diagram, they have written it here. That's it. The same way. There is no difference. So initially, they are sending the MSB bit. That is why it is 1. Okay. So in the first clock pulse, you are putting the information 1 and then it will go to the next clock. That is the next flip-flop, or what you can say it will be in the next clock pulse. You can show the result and you can see the result. And then what happens in the next clock pulse? Again, it will move here. Okay. And then initially you are taking the bits as 0, 0, 0, 0. So other places they have shown 0. Then again you are shifting the bit 1. So it has come, see, they will be coming in the line, right? So this has come now. Then you are going to shift the bit. So finally here they have taken, in this example, they have taken 1101 as an example. You can take any bit and just keep showing the shifting, that's it. Is conversion of one flip-flop to another flip-flop there in syllabus? No. It's not there. Converting, as of now, registers, concepts are there. Huh? It's not there, Anna. It's not there. Okay. Then break kodla. ಇಲ್ಲ ಇದು ಜಾನ್ಸನ್ ಕೌಂಟರ್ ಇದೆ ಒಂದು ಕೆಲಸ ಮಾಡೋಣ Next, we need to discuss on counters. So we shall have a short break. Please come back by, now it is 12:15, right? Come back by 12:25. We shall start discussing on counters. When L is 1, what will happen? Nishant. Where you are asking, Nishant, where L is equal to 1? Q1 ಗೊತ್ತಾಗ್ತಾ ಇಲ್ಲ. What is that Q1? Where actually which place you have the doubt? Wait. Which place? In PIPO diagram? In PIPO diagram. In PIPO diagram, this diagram, right? Nishant. What is the confusion here? Q0, Q1, Q2, Q3 are there. Q0, Q1, Q2, Q3 are outputs. See here, parallel in, parallel out it is. Here you are loading the data parallelly. D3, D2, D1, D0, you are loading it parallelly. Right. Then Q0, Q1, Q2, Q3, you are getting parallel output. Here you are shifting the data serially. The output at the end of the last flip-flop is given as the feedback input. D0, D2, D3, they are considered when we make the multiplexer input, that is the different combinations are there, right? SH and L. This is SH and L. If you take like this, 0, 1, this is SH and this is L. When SH is 0 and L is 1, when that is selected, when you make SH 0, L 1, then the data in the D3 will be loaded to 0, 1. When you want to load something, to the flip-flop, then you need to give SH 0, L equal to 1. Then it will be loaded. And you know that the output of this multiplexer is given to D flip-flop. What is the value loaded? It is the input what we give to D3. D3, whatever that is there in D3, it can be either 0 or 1. Whatever the input is that is given to D3, that will be loaded. Okay, so we shall have a short break and we'll come back by 12:25. Got it? Any doubts? If you have observed the trainer kit, we give inputs, right? We give input set is only there. Output set is only there. We are giving input to the input set. In the timing diagram, that value is considered. See, the timing diagram, whatever they have given in your book down, it is for some particular example. Suppose you want to load 0010 or 1101. Okay, so that is how you are going to get. No, there is no timing diagram for Q1, Q2. You are going to get the, you are going to see the timing diagram for D0. See, I will show you it. Here, you are giving the inputs, right? The input is given here. And based on the input what you give here, you are going to get the timing diagram for Q3, Q2, Q1, Q0. How the data keeps shifting. So you are writing the timing diagram for Q3, Q2, Q1, Q0 based on D0, D1, D2, D3, whatever you give. You cannot separately write timing diagram for Q3, Q2, Q1, Q0 unless you shift something, unless you load something through D1, D0, D1, D3, right? The loading happens when L is equal to 1. Okay, thank you. We will meet by 12:25 or 12:30. And we'll discuss on counters. Okay, okay, thank you.
ಕ್ಲಿಯರ್ ಇದೆಯಲ್ಲ ಅದನ್ನ ಕ್ಲಿಯರ್ ಅದು ಇದು ಮಾಡಿ.
All of you, please join back. We will give you lunch break by 1:30 p.m. Lunch break 1:30 to 2:30 2:15 ಕೊಟ್ಬಿಡೋಣ. I hope all of you are there. Another half an hour, 40 minutes topic is there. After that, we'll give you lunch break. Is it fine? Okay. Yeah, please call your friends back. We had some work, so it became a little late. We started. Okay. So now we move on to the next concept called counters. Counters play a very important role, and they are the applications of registers, applications of shift registers. the name counter helps us to understand the meaning of the word. So what is a counter? Can anybody tell me? If you have studied counter, why do we use counters? Why do we use counter? Counters, yeah, repeats the states in an order. Okay, Nishant is telling that. Next, any other answer? Counter is used to count the number of clock pulses. Actually, we are going to see how many clock pulses have occurred, how many clock pulses a particular process has taken to finish that complete process. So it is used to count the number of pulses. Counter counts the number of pulses. In the previous example, you might have observed that T0, T1, T2, T3, T4, T5, right, in this wave diagram. So it has taken 4 clock pulses to finally give you the output. So it has taken 4 clock pulses. Like that, counter helps us to know how many clock pulses are required to perform a particular operation so that we are going to get the required result. Okay. So this is one of the applications of registers. Counters are applications of registers. One such counter is given as example here. It is called switch tail counter or Johnson counter. The other name for this is switch tail counter or Johnson counter. The switch tail counter, your voice is breaking. Now can you hear me properly? Is it fine? Okay. I think it is fine. Okay. So switch tail counter or Johnson counter. The switch tail counter works in some manner. That manner is shown here in the form of state diagram. You can see how the switch tail counter works in the state transition diagram. So here you are having all the 3 bits set to zeros. Okay. So in the next state, you can see 1, 0, 0. In the next state, you can see not audible. Am I not audible? Even now? 1 second, I'll check the net. 1 second. Now you please check. Am I audible? Okay. So here they move from 0, 0, 0 to 1, 0, 0, then 1, 1, 0, then 1, 1, 1, 0, 1, 1, 0, 0, 1. It is following some rule to move from one state to another state. What is that rule? We shall find out. So initially it was in 0, 0, 0 state. Suppose I'm starting from here. Then it will move on to 1, 0, 0. How do you get this? You need to take the complement of the last bit. Suppose I name them as Q3, Q2, Q1. I'll take the complement of the last bit. I'll take the complement of Q1 and I am going to put it to Q3 like this. So what will happen? It will come here 1 and this will move here. So this will become 0 and this moves here and this will become 0. You have to take the complement of LSB and then give a feedback. Send it in the form of a feedback to the first bit, that is MSB bit Q3. So then you are going to have 1 here. Then the next state is take the complement of this one. Q1, the last bit that is present here. What is the complement of 0? It is 1. So it comes over here like this, and this shifts here, and this shifts here. Getting? Like that. Again, you have to proceed. So take the complement of this and give the feedback. So what's the complement of 0? It is 1. Then this will shift here. So it becomes 1. And this shifts here. It becomes 1. So we are in this state now. Right? I hope you are understanding. Similarly, you can try for the next 2 states. Can you try for the next 2 states? What is the use of we build this counter? Yeah, this counter actually in the previous syllabus, it was a lab experiment. And basically you have seen the serial set lighting, right? LED lights, right? They glow in some particular form. Have you observed that? Certain colors will get on for some time, and after some time, some other colors will be switched on, right? So we want to make that the lights to glow in a particular manner. So we need to follow some sequence, right? To follow that sequence, we use different types of counters. So based on what type of counter we are using, the sequence is followed. Okay. You have seen the traffic light display, right? It will be counting in the descending order, right? Before allowing you to cross the road, right? So how is it possible? There also we are using counter. It's a different type of counter along with the 7-segment display. You can make a mini project with your counters and 7-segment display, right? You can make the traffic light signal, isn't it? And you can use LED to show the red light glow, green light glow, orange light glow, right? You can use your LEDs. So you can form a mini project with this, with the 7-segment display, with the counter, IC, and with the LEDs. Yes. Yes, Jai Shubha ma'am explained how a 7-segment display works. So you can, yes, it is correct, Nishant. So this is how the counter moves from one state to another state. These are all called state. So this diagram is called state graph diagram. In university question papers, they ask you to write a state graph diagram for a particular counter. Okay. So I hope you understood this diagram. How you got this, right? So you can write the truth table for this like this, Q3, Q2, Q1. And write whatever you get here like this 0, 0, 0, 1, 0, 0. That's what I explained here, right? You have to write this truth table. And we are constructing this counter with 3 flip-flops. So we are using D flip-flop to construct the counter. Why are we using 3 flip-flops? Because we are using 3 bits here, right? We are using 3 bits. Suppose I want to make it work with 4 bits. I need to use 1 more flip-flop. Remember, Johnson counter or switch-tail counter is not only confined to 3 bits. You can use 4 bits also. Then coming to this diagram, you can see the 3 flip-flops, D3, D2, D1, right? And you are giving the clock input, and you can see a feedback circuit from Q1 dash to D3. Why is it so? Relate that to the truth table, whatever I wrote now. Why is it so? Why are we giving a feedback from Q1 dash? Because we are taking the complement, right? Complement of the last bit, and then we are giving it as a feedback to the first bit. I hope you are getting. We are taking the complement of the last bit, and whatever the complement we are going to get, we are giving it to the feedback to the MSB. And this bit shifts here. So that is why we are using this feedback. So the explanation of the counter is given here. I'll erase this 1 second. It is an important question. Many times they have asked you to explain the working of switch tail counter or Johnson counter. A fixed sequence of states is called a counter. So you have a fixed state of sequence, a circuit that goes through a fixed sequence of states is called a counter. So when does it goes through the fixed sequence of states? When does it go through the fixed sequence of state? When the clock pulse occur, right? The state changes in each clock pulse. Okay, so the clock pulse is related to the state. A shift register with inverted feedback, that is very important. A shift register with inverted feedback is often called a Johnson counter or twisted ring counter. Okay. A shift register with non-inverted feedback is often called a ring counter. A ring counter, they have not explained in this book, but if you take without twisted feedback input, suppose you take from here like this. Sorry. If you take from here like this, it becomes a ring counter. In ring counter, I'll just explain you the truth table of a ring counter. I'm explaining the ring counter concept, ring counter. In ring counter, if the initial state is 0, 0, 0, okay, and then the next state, suppose the initial state, wait, I'll take it as 1 second to show you in a better way. If the starting state is 0, 0, 1, what happens? This 1 will come here, then it becomes 1, this 0 moves here, and this 0 moves here, so it comes like this. Then again, you are not taking the complement of the last bit, you are just sending last bit as a feedback to the Q3. Okay, so then this comes here, and this comes here, and this comes here. Okay, then again you are going to take the feedback like this. Then you can only tell me what is the result of the next step. What's the next state? Can you please tell me? The next state is very good. This comes here, so it is 1, 0, 0. So this is ring counter. In lab experiment, this concept is there. We can actually see how the counter works. If you take Q3, Q2, Q1 has output, you can see the bits shifting, the LEDs shifting, the glowing of LED, it shifts from one place to another place. Once this will be on, others will be off. Then this will be on, this will be off, right? So in each clock pulse, you can see the difference. The bit shifts. Okay. Yeah, the importance is given to clock pulse in counters. Okay. I hope you understood both switch tail counter and ring counter. Is it fine? They are important questions. So for this, can you write the waveform? Can you try to write the waveform for the switch tail counter? How will you write the waveform? Yeah, I hope you have written the truth table. Try to write the waveform for that. So I'll once again write the truth table. It is 0, 0, 0, 1, 0, 0, right? 1, 1, 0, 1, 1, 1, 0, 1, 1, 0, 0, 1. This is Q3, Q2, Q1. So for this, you need to write the waveform. I'll show you here only how to write the waveform. So first, I need to take the clock pulse. So I'll take the clock pulse. So this is clock. Then what I need to take? I need to show Q3, Q2, Q1, Q0. Since I have taken non-inverted clock, so I have to take the rising edge. I have to consider the rising edge of the pulse. So I'll write a dashed lines dropping down from the rising edge. I'm taking the dropping down from rising edge. Okay. Now we shall write the waveform for Q3, Q2, Q1. Okay. So first we'll write the waveform for Q3. So you just see the column for Q3. What is there in Q3? In the first pulse, it is 0. Okay. Then next rising edge you need to take, then it becomes 1. Okay. And in the next rising edge also, it is 1. Right? And in the next rising edge also, it is 1. This one, you see this 0, 1, 1, 1. Then in the next rising edge, it becomes 0. So this is how you need to write. So you wrote for Q3. Now you can write for Q2. You can write for Q2. See that Q2 column. After seeing the Q2 column, you can write. Yeah, delays you can show. Delays you can show. Here, in a very apt way, I cannot write. So I'm writing with this board, right? You can show the delay while writing in an exam. Show little delay. And in Q2, so it is 0, 0. Right here, see the delay. Then here I'm showing little delay also. Then it is 1, 1, and then 0. That is 0, 0, 1, 1, 0. Okay. Here delay is there. Okay, I have given delay here also. You can see it is delay is there. Then Q1. Q1, how are you going to write? So 0, 0, 0. Okay. So in the first pulse also it is 0. In the second also it is 0. And here also it is 0. So then it becomes 1. Give some delay. Give some delay. And then show 1. So this is how you need to write the waveforms for the Johnson counter or twisted ring counter. It's also called switched tail counter because you are going to switch the tail to another mode and then you are pushing it to the first bit. So if you follow the same method, you can easily write the waveforms for ring counter also. Okay, ring counter state graph will be like this: 0, 0, 0. It will go to 0, 0, 1. Then it will go to what? 1, 0, 0. Right? Are you getting? Then it is then it is what? 0, 1, 0, and then it is 0, 0, 1, okay, like this. you can show you can continue like this. If you take this here, you should take it as 1. Okay, 0, 0, 1. Or else once again, the initial state, one second, I'll show it once again. I'll show it once again, 1 second. So here, you take it as the initial state as 0, 1, 0. If you take this as initial state, then it will go to 0, 0, 1, and then it will shift, right? So then it will be 1, 0, 0. So then it will go to what? 0, 1, 0. It has come to 0, 1, 0. So directly you can connect it. So it has, the next state is 0, 1, 0. You can directly connect it like this. So these are the states. 0, 1, 0, 0, 0, 1, 1, 0, 1. Next, it is coming back to the same state. This is how you need to write for ring counter. This is for ring counter state graph. And for ring counter, what is the difference you need to show? You need to show directly from here a feedback like this. Okay, I hope you are familiar with the concepts now. Okay, any doubts? Surely they'll ask these type of counters. You cannot escape from such questions. Surely there'll be questions on counters. Okay. A few minutes, I am sharing some documents in the screen. Please wait for a few minutes. Yeah. So now we are in the topic design of binary counters. Till now we understood how the registers work and the basic counters, that is switch tail counter, ring counters work. But from here onwards, we ourselves, we design the counters. In the previous cases, we did not design the counters, but from here onwards, we are designing the counters. The question occurs like this: design a particular counter, design a mod 5 counter, design mod 6 counter, design a counter with 3 flip-flops. So the question starts with the word design. And there are two types of counters, synchronous counter and asynchronous counter. So in your syllabus, you have synchronous counters. You have synchronous counters. But you should know what is asynchronous counters also. So asynchronous counters are the counters in which each flip-flop waits for the result from the previous flip-flop, and it is taken as a clock input to the next flip-flop. Basically, the next flip-flop works based on the result, at what time you are getting the result, and that is given as clock input to the next flip-flop. Okay. So there is too much delay in asynchronous counter because of the flip-flops waiting for previous results. Each flip-flop waits for the previous result. That result is given as clock input. Okay. Suppose if the any doubts? 1 second. We don't have asynchronous counter and ripple counter. We don't have ripple counter. Illala. No, that ripple counter is not the. Wait. Ripple counter is not there. It was there in the previous syllabus. The ripple counter is not there now. Okay. Yeah, I hope you have seen the diagram of ripple counter. The output of the one flip-flop, it is given as the input to the next flip-flop. Right? Okay. Synchronous counters means the operation of the flip-flops are synchronized. That is, clock input is given parallelly, simultaneously to all the flip-flops. Okay. So I'll just show you here only. In case of asynchronous, if the flip-flops are connected like this, if they are cascaded like this, the output of the first flip-flop, suppose you are using D flip-flop, the output of first flip-flop, it acts as clock input to the second flip-flop. The output of this flip-flop, it acts as clock input. Once you get the output from first flip-flop, then only the second flip-flop can be activated. Imagine if so many flip-flops are cascaded like this and you want to get the result at the end, there will be so much of delay, right? So it is not that we don't use asynchronous counters. They are used in their own applications. But here we are concentrating on synchronous counters. In synchronous counters, here I'll just show you. In synchronous counters, the clock inputs are given simultaneously. I can say parallelly to all the flip-flops at the same time. You are going to give the clock input at the same time to all the flip-flops. So this is synchronous. This is synchronous counter. And this is how the asynchronous works. Let it be any type of flip-flop, what you use. Okay. The main concept is how the flip-flops work based on the previous result, or clock input is given parallelly, simultaneously to all the flip-flops. So this is asynchronous. This is how basically they work. It is not there for you. You are concentrating on this. Okay. So now coming to the synchronous counters means the operation of the flip-flops is synchronized by a common clock pulse so that multiple flip-flops can change their state simultaneously. You have to concentrate on the word simultaneously. The state of the counter is determined by the states of the individual flip-flops. Okay. So we shall see how binary counter works. We are designing a binary counter. I'll share the screen 1 second. Okay. So synchronous counter means the operation of flip-flop is synchronized by a common clock. Clock is common. That is important. You have common clock pulse, so that when several flip-flops must change state, the state change occurs simultaneously. So this is very important definition. You have to concentrate on this definition. There is no common clock pulse in case of asynchronous. That is why delay occurs. Because of the delay, we use synchronous counters where the delay is less. So this is design of the counter. It's the final circuit what you have got. But before getting this circuit, you have to work on so many things. You can see here. First, you need to write the table, truth table for this. How are you going to write the truth table? Which flip-flop is used here? Which flip-flop is used? Someone has asked a question, ma'am, which has more delay, asynchronous or synchronous? Asynchronous has more delay than synchronous. Toggle flip-flop, very good. So they have used toggle flip-flop. What is the characteristic of a toggle flip-flop? What is the characteristic of a toggle flip-flop? Yeah, come on. Okay, tell me. If toggle is high, what is the output? When input is 1, it toggles. The output changes. If the input is 0, the output, okay. You have to consider like this. As I told you yesterday while doing flip-flops. One second. There is. When toggle is 0, if the state is in 0, okay, the next state will be, what's the answer? Toggle is 0, the present state is 0, the next state is? The next state is 0, correct. Tamanna, you are correct. Arthik, it will not be 1. If the toggle is 0, if the present state is 0, the next state will also be 0. Okay. If the toggle is 0, if the present state is 1, what should be the next state? Yeah, the next state should be 1 because it retains the previous state because the toggle is 0. Suppose I give toggle 1. I give toggle as 1. The present state is 0. What should be the next state? Very good. It should be 1. If the toggle is 1, the present state is 1. What should be the next state? Yes, it should be 0. Now you observe, if the toggle is high, then only the present state changes to some other result. If the toggle is 0, the present state won't change. The next state also retains the previous state. Q plus will have the same value as the previous state. Getting? Okay. So to understand or to design this counter, you should understand the T flip-flop working or T flip-flop truth table. Without understanding T flip-flop truth table, you cannot understand the design. So now all of you are okay with the truth table, I guess. Okay. So now I'll go down here. Now you have to write the truth table considering 3 bits. We are designing the counter for 3 bits. So then how many flip-flops are required? We are designing the counter for 3 bits. How many flip-flops are required? Very good. 3 flip-flops are required. 2 to the power of 3. Right. So since there are 3 bits, A, B, C. So 2 to the power of 3. This 3 shows the number of flip-flops we need to use in the register. Preeti, it is not 8. You should not take 2 to the power of 3 that is equal to 8. No, you have to consider the power. Whatever the power is mentioned, that power is the number of flip-flop. Got it? Okay. So now coming to the truth table, we shall write the truth table like this: the present state, next state. Okay. The present state, suppose you start it with 0, 0, 0. Then what should be the next state? It is just like writing the numbers from 0 to 7. You are writing the numbers from 0 to 7. That is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. So it is 0, 1, 2, 3, 4, 5, 6, 7. Okay. The present state is like this. Then we shall move on to the next column. We are going to decide the next state based on the present state. Just observe what is the present state here, 0, 0, 0. What is the next state for this present state? What is the next state for this present state? Very good. It is 0, 0, 1. So that is what it is being written here. Then what is the next state for 0, 0, 1? 0, 1, 0. That is written here. I hope all of you are getting. What is the next state for 0, 1, 0? It is 0, 1, 1. So it is being written here. All of you are getting? Any doubts in writing this? Present state, next state, truth table? Okay, no doubt. Okay. Then coming to the last column, we are writing this column based on the truth table. Okay. First, we shall observe TC. To get the results in TC column, you have to observe. C column in the present state and C column in the next state. Okay. So when the present state is 0 and the next state is also 0, you have to read like this. The present state is 0. The next state is also 0. Then what should be the toggle? The present state and next state both are same. Then toggle should be 0. The present state is 0 and the next state is 0. What should be the toggle? 0. The present state is 0. The next state is 0. What should be the toggle? 0. The present state is 0. The next state is 1. What should be the toggle? 1, because it is switching its state from 0 to 1. Next, the present state is 1. The next state is 1. What should be toggle? 0, because they are not switching the state. They are in the same state. Right? C. 0, 1 is there, 1 is there. Then here also, the present state is 1. The next state is 1. There is no toggle. Present state is 1. Next state is 1. No toggle. The present state is 1. Next state is 0. So toggle is there. Okay. So similarly, you need to find out the TB column. TB column. Right. It's already done. You just verify with the truth table. I'll better write the truth table here so that later when you see the video, you can clearly understand. Toggle is 0, 0, 0. Then toggle is 0, 1, 1, and toggle is 1. It will move from 0 to 1. When toggle is 1, it will move from 1 to 0. So truth table is written here. I'll clear this truth table. Just verify the column for TB and TA. Are you okay with that, or you have any doubt in that? Yeah, you can use the excitation table for this. You can use, actually, see here, it is like this. It is reverse, right? If C is 0 and C plus is 0, what does the excitation table tell? What does the excitation table tell? It is reverse mapping, right? So the excitation table tells the toggle should be 0. Okay. Then you just keep this. See, that is the present state is 0. The next state is 0. Toggle should be, you'll be guessing what should be there in this. You can use excitation table. Okay. You can continue like this. But without knowing the truth table, you cannot write the excitation table. But for this, you can use excitation table. Got it? So after this, you need to write a map. You need to write map. K-maps. So characteristic table is also given here. So this yesterday Jaishubha ma'am has explained the state transition diagram of toggle flip-flop, and characteristic equation also she told how to get yesterday. So this is how it is written here. And coming to this, you need to write the map, K-map. So how are you going to write the K-map? How are you going to write the K-map here? MSB is taken at the top, that is C is taken this side. So the numbering changes. So in this case, the numbering is like 0, 1, 2, 3, 4, 5, 6, 7, right? So fill for TC, whatever you have got in the column TC, in the TC column, whatever you have got, fill it. Then TB column, whatever you have got, fill it. Then TA, obviously TA, it forms what? K-maps. TA forms a octet. So the answer will be, since it's a 3 variable map, answer will be 1, direct answer. It's a octet. Now, what is the answer for TC and TB? Can you find out? You can form in the other way also, the K-map. Okay, you can form the K-map in whatever manner you are convenient with. So for TC, the K-map is written. You're just filling it, that's it. And for TB, you have written. So whatever the equations you got for that. So TC you will get as what? BA. TC you will get as BA and TB, A. All of you got this? Directly you can tell. Yes. And what about TA? TA is 1 because it forms a octet. Okay. So after getting these equations from the K-map, you need to draw the circuit diagram for this. Okay. So you remember what you have got. TC is BA and TB is A. So now I'll go up and I'll draw the map here. Now circuit diagram here. Okay. So we need 3 flip-flops, right? 3 variables. Then since we are using T flip-flop, we are representing that with TA, TB, TC. Now how to make the connections, right? Before making connections, we shall give the clock input. The clock input is given. This is clock, right? It is not an inverted clock. It's a direct clock what you are giving. Now we shall observe the equations what you have got. Okay. So what is TA? TA is 1. So you can observe here TA is connected to 1. That is high. Got it? Then what is TB? TB is equal to A. So take a line from TB like this and connect it to A like this. and connect it to A. Getting? Then what is TC? This one, TC. TC is B and A. If nothing is mentioned here, it is by default AND operator, right? B and A. So here we are using a AND gate. Okay. B. This line is from B. You can observe this line is from, sorry, this line. This line is from B and this line is from A. So here it forms B and A. So that is given to TC. TC equal to B and A. So this forms the design. So based on the number of bits you have taken, you are going to design. Okay. So like this, they can ask you the direct question to design binary counter. Binary counter that is starting from 000 to 111. It's a direct question. Sometimes they can ask you with the different states. So that also you can do it. In the previous university question papers, they have asked you the different states. Solve ಮಾಡ್ತೀರಲ್ಲ different. Thank you. We will join back by 2:15. If you please join, dear students.
Hello, all. Good afternoon. Hope all of you have joined back. So we'll start with the next session. Am I audible? Can you all listen to me? Yeah. Okay. So I'll just recap the steps for the design of synchronous binary counter. So I think in this slide, the main steps, the three main steps for design of any flip-flop, for any, just a minute. So you have to design a synchronous counter using any flip-flop. You can design a synchronous counter using any of the 4 flip-flops which are available, right? The first one here was to design a synchronous counter using T flip-flop. So it need not be always T flip-flop. It can be any flip-flop like SR flip-flop, D flip-flop, or even JK flip-flop. So here the steps are given for designing using any flip-flop. So first step is these are the 3 main steps. So in that, the first step is create state table with present state, next state, and flip-flop inputs, right? So this is the state table. So you can see here, this is the state table, and the state table will have 3 main parts: present state, next state, and flip-flop inputs. So while creating this, you need the help of this excitation table. Present state and next state you can write by yourselves, but while writing the flip-flop inputs, you need to refer the excitation table. So after doing this, then put the inputs in the K-maps, and through the K-maps, derive the input equations, right? So these entries, whatever you write here, the inputs, these have to be individually entered in each K-map, and you have to derive the equation. And after that, after deriving the equation, you have to draw the counter circuit with the derived equations and show the inputs and outputs. So these are the main steps for designing a synchronous counter, right? So here, these are the detailed steps of creating the state table and to derive the equation. So that will anyway be seen while we solve the problem, right? So this was done. And next, so here the question is synchronous binary counter using D flip-flop. The same counter, whatever you designed using T flip-flop, here it can also be designed using D flip-flop. So this is the next example. So design a synchronous counter using D flip-flop. So for this, you have to follow the same steps to redesign the binary counter using D flip-flops. Or one more way to do this is to convert each D flip-flop to a T flip-flop by adding an XOR gate. See, the T flip-flop, whatever you have got here, this same circuit can easily be converted for a D flip-flop by just converting, adding an XOR gate as shown in the following figure. So you can convert a T flip-flop to a D flip-flop by adding a XOR gate as shown in the diagram below. So did you all understand what I am telling? So how to do, we'll see it here. So just add an XOR gate along with the equations whatever we have derived for T flip-flop. Along with that, you just have to add a XOR gate. Hence you have the 3 XOR gates here, right? The rightmost XOR gate can be replaced with a inverter because A mod 1 is A. So this symbol plus encircled is nothing but it is a symbol for the XOR gate. Whenever you see this symbol plus inside a circle, then it is for XOR gate. It is also called as A mod B. So this symbol is called as mod, right? So now these are the equations for the D flip-flop. So DA equals A plus. What is A plus? Are you listening? What is A plus, B plus, and C plus? Can anyone answer? Next state. Very good. So A plus, B plus, and C plus indicate the next state. So here in a D flip-flop, A plus equals A dash. So A dash can be shown with respect to a XOR gate. XOR gate is also like a universal gate which can be used for realizing any other basic gates, right? So it can be used for realizing a inverter. I think A mod 1, just a moment. Yeah. So can you all hear? Can you all hear? Yeah, I had just muted my mic. I had something here. So I just muted it. So now you can hear, right? Okay. So here we can convert the D flip-flop to a flip-flop by just adding a XOR gate. So how is it done? So for the rightmost gate, here you can see that the rightmost XOR gate can be replaced with a inverter because A mod 1 equals A dash. So this is just represented as A dash. So whatever is in the brackets here, A mod 1 equals, I have just written it as A, you just put it as A dash. So here it is correct. dA equals A plus, which is A dash, right? And dB, see here, if you want to have the proof of this, you can just write down the truth table for a D flip-flop. For a D flip-flop, you know that whatever is the input, output will also be the same. See here, I just tell for the last state, I mean for A, later you can go through it, right? You can do it in the same steps. See if it is, see here, the truth table is for the presence, what is it? State table is for T flip-flop, right? But when you have to write it for a D flip-flop, I'll just show for DA. What is the definition of DA? DA means for a D flip-flop, the output is same as input. So whatever is the next state, whatever is the next state here, the input also should be the same. So what will be the input? Input will be 1 0 1 0. Whatever is the output, same thing will be your input. But here, what was TA? TA was completely, TA is the opposite of it, right? If we want the output to toggle, if it is compared with, when we compare TA, if the present state is 0, next state should be 1, means the input should be 1. Whereas for D flip-flop, whatever should be the next state, the output should be the same. So hence here, because the output should be same, but here we have 1. So it has to be inverted. So for TB, you can see that the inputs are inverted when compared to DA, right? It is just the opposite of DA. So there we can use it as inverter because we are converting a T flip-flop to a D flip-flop. So I'll go to the next one. Yeah. So DA equals A plus, the next state should be A dash. So as we saw in the 2 table, the output will be just the opposite of A dash because for T it was reversed, but for this it will be back to the other one. Whatever was A, it will be the same thing. So it is given as A dash, right? Then for DB, it is the next state for D flip-flop is B A dash plus A dash B, which is nothing but B mod A. So this mod is B XOR of A. And for DC, it is C plus, which is next state, which can be derived by C dash BA plus CB dash plus CA dash. And this is again factored as C mod BA. So all this is derived by the equations from the next step. You just have to write the state table, check the inputs, and when you compare the inputs with the T flip-flop, then you will get this equations. So instead of getting all these equations, generally when you want to convert a D flip-flop to a D flip-flop or a counter using T flip-flop to a D flip-flop, as we have done here, you can just write that including XOR gates for each of these blocks, it can be converted from T flip-flop to D flip-flop. You need not show the derivation. If the question is for show the T flip-flop and then show the D conversion. So if it is that way, if they have asked for conversion, then you can show, you can just have this sentence, write this sentence and show the diagram. So here you can see that each of the inputs for A, B and C, the first gate is XOR gate. The XOR gate is included and then whatever is here is the same as your T flip-flop. So TC has, what is this, A dash A and B. So same thing is here also. DC has AB, right? A and B, which is XORed with C, XORed with its own output, right? So this is the way of converting the synchronous T flip-flop into a synchronous counter using D flip-flop, right? So next we'll go to the next type of counter which we have to design. So that is binary up-down counter. So here the state graph and the table for an up-down counter are shown in the following figure. So this is the state graph and this is the state table. So right, so this is the state table here. This is the present state. These two are the next states. This is for wherever you see U, that is for up counter, and this is for down counter. The column below D is for down counter and column below U is for up counter. So up down counter means the counter should be functioning for both up count and down count. Up count is to count from 0 to 7 and down count is to count from 7 to 0, right? 7 to 0, it has to count from 7 to 0. So we'll see how to do it. So here, when U is 1, the counter counts up sequence. So you have two control signals, U and D. When U equals 1, the counter will count in the up sequence, that is 0, 1, 2, 3, 4, 5, 6, 7, and immediately after 7, 0. Right? Then when D is 1, if the control signal D is 1, then the counter counts down in the sequence 0, 7, because after 0, the next down count will be 7, 6, 5, 4, 3, 2, 1 and 0. Right? When both are 0, when up U and D both are 0, the counter state does not change. It remains in whatever is the current value. It will not change. And both cannot be 1 at the same time, because the counter can either function as a up counter or as a down counter. No counter can definitely count as both up and down counters. It is like climbing and getting down the stairs at the same time. A single person cannot climb up as well as climb down at the same instant, right? So similar to that, you can never have U and D as 1 at the same time, right? So here you have the state graph where it shows. So this arrow mark tells you the direction. So wherever you have U, that arrow mark is for up counter, the outside circle is for up counter, and the inside circle is for down counter, right? So up counter after 0, it counts 1. So up counter, yeah, sorry, I had to mute it. Some other disturbance was there. Okay. So inner circle. Inner circle is for down counter, while the outside circle is for up counter. So this sequence is given here. So we'll see that state table. So in the state table, the first column is for present state, and these two columns is for next state. The first one is for up counting, and this is for down counting, right? So now here I'll just read out this. By inspection of the above table, we can derive the equations for a down counter. So this is the table. In this, by inspection, just by seeing the values of the present state and the next state, he is telling that we can derive the equations for down counter, right? So we'll see how the inspection is done. So for every row of the table, A plus equals A dash. So wherever A plus equals A dash, so A changes state every clock cycle. So for those rows where A equals 0, B plus equals B dash. So here, from here you just observe for every row of the table, A plus equals A dash. So I'll just mark them and show you. See here, yeah. So this is A and this is A plus for the down counter. So if you observe for every row, wherever A is 1, say here first row A is 0, whereas D is 1. Next row A is 1, whereas D is 0. Here A is 0, D is 1. So if you observe this complete column of A and A plus of the down counter, you can observe that both are opposite, right? Both are opposite. Hence, we have the equation as A plus equals A dash. So for A plus of the down counter, that is next state of the down counter, it is A dash. The equation will be equal to A dash. And next, so A changes state every clock cycle. Means A will change its state for every clock cycle of the down counter. Then for B, we'll see what is happening for the B. So for those rows where A equals 0, B plus equals B dash. So which are the rows where A equals 0? Just clear all this so that now we'll compare for B, right? So for those rows where A equals 0. So where are the A is 0? So this has a 0, this has a 0, this has a 0 and this has a 0. B plus equals B dash. Where is B plus? B plus is here, right? What is the value of B? B plus equals B dash. So here B is 0, B plus is 1. Similarly here B is 1, but B plus is 0. Are you all observing? Here B is 0, whereas B plus is 1. And here B is 1, but B plus is 0. So you have to carefully read these equations and then observe the columns, right? So it says for those rows where A equals 0. So first you have to mark the rows where A is 0, right? And then compare B. Mark the rows where A equals 0. But what should you compare? You should compare B. You should not compare A. You should compare B. So what is B at the position where A is 0? B is 0 here. What is B dash or B plus? B plus is 1. Similarly here, B is 1. B plus is 0. Here B is 0. B plus is 1. And here B is 1, whereas B plus is 0. Right? Whereas for the other entries, it is 0. B is constant for the other positions. It will not change. Only the points wherever the output is changing, those are given in the equation. Wherever it is not mentioned, those input and output will be the same. Only the for the clock cycles where the output will change, only for that the equation is given. So B plus equals B dash, wherever A is 0, B plus equals B dash. Then now similarly for C. For the rows where B equals 0 and A equals 0. So now you have to check two possibilities. You have to check wherever B is 0 as well as A is 0. So what is the output? C plus equals, I think this is also C dash. So we'll just observe here. So now I'll clear all the drawings of B. So now we have to check for C. Wherever B is 0 as well as A is 0, C plus equals C dash. So in this B is 0, A is 0, and here also B is 0, A is 0. So what is the value of C? This is 0, whereas C plus is 1. So this is C plus equals C dash, right? So wherever A and B both are zeros, in those rows, C plus equals C dash, right? Similarly here, where A and B both are 0, C plus is 1, whereas C is 1 and C plus is 0. Understood? But for the other rows, the input is same and the output is also same. Did you all get this? Did you all understand this? How to inspect and get the equation? TA, I didn't understand. TA for the T flip-flop. See here again we are doing, right? So whatever we get here for D in the, is it TA or DA, Manoj? I think this was in the morning. Okay. Ma'am, can you explain once again, ma'am? Which one, Manoj? Which one you want me to explain? Now, present form. Okay, I'll do it. So I'll just clear all this, start from the beginning, right? Yeah. So we can, by inspection method, how to derive the equations. So here we are seeing by inspection method, how the equations can be derived. So using inspection method, derive equations, right? For a down counter. First is for a down counter. So we have to observe each row. Each row we have to observe with respect to, first is with respect to A. When A plus is the next state, next state will be equal to A bar. For every row of the table, see, for A, this is A. Last column is A. So now we have to compare only the present state and the next state for a down counter. Please remember that this is the down counter next state. Got it? Last column is the down counter next state. So here you can observe that for every row where the present state is 0, next state is 1. So here present state is 1, next state is 0. Present is 0, next is 1. So like that it goes on inverting. If the present state is 1, the next state is 0. If the present state is 0, next state is 1. Hence we write the equation as A plus equals A dash. A plus is nothing but the next state. So next state for A is always A bar or A dash. Right? Did you understand for the first one? A? Yes, did you all understand for the first one? How to derive the equation for A dash, A plus? Okay. Next, now we have to see for B. What will be the equation for B? So for B, we have to first check wherever A is 0. So you have to mark the rows wherever A is 0, but do the comparison for B. Mark the rows wherever A is 0, but do the comparison for B. What is B? B plus equals B dash. B plus means next state. So this is the next state. So at this position, for B it is 0, whereas B plus is 1. Present state is 0, next state is 1. Similarly, for this row, present state is 1, next state is 0. Here, present state is 0, but next state is 1. And here, present state is 1, but next state is 0. So if you observe, wherever A is 0, B plus is a B dash or complement of B. Got it? So you have to mark the rows under A wherever it is 0 and write the equation for B. So this is the condition. If A is 0, then B plus equals B dash. This is the condition, right? Else B plus is same as B. See, wherever A is not a 0, B plus is same. Got it? Wherever is not a 0, B plus is same. It is constant. It will not change. Hence, we are not considering that. So understood for B now? Got it for B? Yes. Next. So next we have to check for C. Similarly, we have to check for C. So what is the condition for C? You have to check for the rows where B is also 0 and A is also 0. So where are both 0? In the first row, A is also 0 and B is also 0. Similarly, in the fifth row also, A is also 0 and B is also 0. So at this position, if you observe, if C is 0, C plus is a 1. If C is 1, C plus is a 0. So it is complement of C. Wherever A and B both are zeros, C plus equals C dash. C plus equals C dash. So here you have two conditions. When B is 0 and A is 0, C plus equals C dash. But in the other positions, you can see that the C plus is same as C. C plus is same as C. You can observe that C plus doesn't change in the other positions, except wherever A and B both are 0, it will be opposite of C. Understood? See? So now all the equations are clear, right? So shall I move on to the next slide? Okay. So next. Next is the same, the equations, whatever we have designed, now we have to implement in the form of a circuit. So the equations for up counter are as shown. So this we saw when we had to convert from T to D, right? When we converted the T flip-flop of the up counter, we converted using D by adding the XOR gates. So that we can, the same equations are considered here, right? Now when U is 0 and D equals 1, these equations reduce to. So, and here when U equals to 1 and D equals to 0, these equations reduced. So these are the two conditions. So what does the condition tell? If U equals to 1 and D equals to 1, the counter will act like what? This is the counter which counts both up and down. That is, either it will count as an up counter or it will act as a down counter. So at any instant, it can either work as up counter or down counter. Parallelly, it can't do both. So what is this indicating? Is it working as an up counter here or down counter? That is, when U equals to 1 and D equals to 0, what does it work like? Does it work like an up counter or a down counter? So what does it work like? Up counter, correct? So it works as a up counter whenever U equals to 1 and D equals to 0, right? So next is when U equals to 0 and D equals to 1, what does it work like? When U equals to 0 and D equals to 1, it works as a down counter, correct? So when U equals 1, it works as up counter, and these are the equations which we already saw in the previous exam. And when U equals to 0 and D equals to 1, it works as a down counter. So for this, we just, in the previous slide, using the inspection method, we got this. dA equals A plus, which is A dash, right? We got it as A dash. And dB equals B plus, which is nothing but B plus A dash. So we had the condition that, what is the condition here? For the rows where A equals to 0, B plus equals B dash. So that when we put it in the form of an equation, it becomes as B mod A dash or B XOR A dash, right? B changes when state A equals 0. B changes state whenever A equals 0. So this is written in the form of equation as B XOR A dash, right? And then for DC, what will be the equation? C changes state when both A equals to B equals to 0. Both have to be 0. At this instant, C will change its state, means it will become complemented. So this, when it is written in the form of equation, it is C mod B dash A dash, right? It is nothing but C mod B dash A dash. So if you observe here in the down counter and up counter, in down counter, dA is same as up counter, whereas in down counter dB is B mod A dash and in up counter it is B mod A. And for DC, in down counter it is D mod, C mod B dash A dash, whereas here it is C XOR of B into A. So almost everything is similar. except we have the complement of A for DB and complement of all the variables for DC, right? So now when we combine it, when both have been combined, because to write the circuit, you should write it as U plus D. So here for DA, A plus is the next state, which equals A mod U plus D. So you are having this U plus D, right? And here it is B mod UA plus DA dash. For DB, for the second flip-flop, for the B state, B plus state, it should be B mod UA plus DA dash. See, for up counter it is A, and for down counter it is A dash, right? As it is UA plus DA dash. And then here it is A dash, right? B is common, so B is removed. Here it is A and here it is A dash, so that is written as A dash. So here it is UA. B is taken as common, so U into A, it counts as up counter when A is without a complement, and it counts as down counter when A is with a complement. Hence it is written as B mod of UA plus DA dash. So it is nothing but adding up these two equations. These two equations have been added. So here B is same, right? Hence B is taken as the common. And here, when does it count as up counter? If the output is A, it is counting as up counter. That is, here U is 1, so it is U into A. Whereas here D is 1, so it is D into A dash. Similarly here, here it is A dash U into A is common here, so it is A mod of U plus D, because both are same. So this, I think it should be here A dash U plus D. And here for C it is C plus. So C is common, right? Here also you have a C and here also you have a C. So that is common. And then what is left out here? This is BA into U. So it is UBA. And then here you have B dash A dash into D. Hence it is D into B dash into A dash. So this is the final equations for you to write the circuit diagram, right? So here, now how to write the circuit diagram? DA. This is the flip-flop for the A bit. So what is the flip-flop? What are the circuits? A XOR U plus D. So here you need a OR gate, and for this you need a XOR gate, right? So here you need a OR gate, and here you need a XOR gate. So this is for XOR and this is for OR gate. Hence, so in the circuit you have a OR gate for the sum of D plus U. You have OR gate, and output of the OR gate is given as one of the input for the XOR gate, and the other input is from its output. Because it is A dash, this will be functioning as an inverter, hence it is given as A here. Output here will be A dash, right? Output of this XOR gate will be A dash. And next, for DB, what will be the circuit for DB? So here you have two AND gates, right? UA is through an AND gate, and again D into A dash also needs a AND gate. So here you have U into connected to A here, U is connected to A if you see here, right? U is connected to A, and D is connected to A dash, plus D is connected to A. This is connected to D. So this is the connection for the two AND gates. Either you can show these connections if you are able to show it easily, or you just write the input values here. So instead of writing all this connections, because it may lead to confusion, you can just write the value of the input here. Here you can just write it as A, and here you write it as A dash. Right? You just mention the inputs here, and no need to show this line also. You don't no need to show this line at all. Right? So this is for these two. So now we have done these two. Then again, what is the gate required here? So you need an OR gate to combine these two. So this is the OR gate. So output of DA dash plus output of UA is connected to OR gate, and output of this is connected to the XOR gate. Output of this is given to the XOR gate, and again XOR gate should work as an inverter, so it is connected to B. So here you have a, understood? And next, so now you have to have a 3-input AND gate for this term and one more 3-input AND gate for this term, plus an OR gate similar to whatever we did here, and that is in turn connected to a XOR gate. Thus we write the circuit diagram for these 3 equations for a up-down counter. So now whenever D equals 1, if I give 1 here and 0 here, what will the counter count as? What will be the counter counting? Will it be counting as up counter or down counter? When the value of D is 1 and U is 0. Now at the inputs, so again it will start counting down. If I change it as D equals to 0 and U equals to 1, it will start counting as a up counter. You need not do any changes in the circuit. So it is a common circuit for both to work as an up counter or a down counter. The only change you have to do is either of these have to be high. Either D should be high or U should be high. If U is high, it will work as a up counter, and if D equals to high, it will work as a down counter. So got this? Up down counter. Understood? What happens if we give D equals to 1 and U equals to 1? So this is not permitted, it is not allowed at all. It is like, can you count together? Suppose I'll ask you to count from 1 to 10, both up and down, not one after the other. Parallelly you have to count. Is it possible? 0, 1 you should tell, and 1, 0 you have to tell. Then how will you go above? You cannot, right? So both can never be 1. So this is like the forbidden state of your SR flip-flop. So both can never be 1. If both are 0, 0, it will not change. But both cannot be 1. If both are 1, the counter again, it will not count, or it will go into a hanging state. It will just stop working. Got it, Siddharth? Okay, any other doubts? So shall I go further? Okay. So I'll just clear all this. Next. So next is design of an synchronous counter using SR flip-flop. Design a synchronous counter using SR flip-flop. So this is similar to your first flip-flop, whichever Shalini ma'am taught pre-lunch. So the same steps have to be followed. Here, the only difference is that for SR flip-flop, you have 2 inputs. For an SR flip-flop, you have 2 inputs. So for each state, that is for the current state and next state, you will have 2 inputs, because there are 2 inputs for a SR flip-flop. Got it? Because for an SR flip-flop, we have 2 inputs. Here, if you observe, something went wrong with this pen. It's not. So now here you have to design a SR flip-flop for a synchronous counter. Using SR flip-flop, you have to design a synchronous counter. The steps remain the same, right? But you just have to try. So I have used a excitation table of the SR flip-flop, and here you have the present state for SR flip-flop for a counter and the next state for the counter. So I have given the empty columns here so that you people can try. So now I'll just show for one set, then you can do it for the other. So I'll show for C, then you can try for B and A, right? So now the current state for C is 0 and the next state for C is C plus. So what should be the inputs at S and R? So now I have to write the input in terms of 2, whereas previously for T flip-flop we wrote only for 1 because it had only one input. But for an SR flip-flop, you have 2 inputs, right? Got it? So what should be the values of S and R? So if the input has to be same, if it is 0 at the present state and 0 at the next state, then the SR should be 0x. You can observe here, if the current state is 0 and the next state is also 0, then inputs should be 0 and x. So here I have to write it as 0x. Got it? So compare for each value of C. So go column wise, finish for each column, each input, then you can easily do it. So here 0, 0 again. So what will be the input? It will also be 0x. Next is also 0, 0. So this will also be 0x. And next also you have, next is 0, 1. So now current state is 0, but the next state should be 1. So if current state is 0 and the next state should be 1, what is the input? It should be 1, 0. So write 1, 0 here. Got it? And here it is 1, 1. Current state also 1, next state also 1. So if both have to be at 1, then the input is x, 0. So here also it is again 1, 1. So there also the inputs are x0. For the next also it is same. It is at 1, 1. So the inputs are x0. And here for the last one it is 1 present state and 0 is the next state. So when the input is 1 and 0, sorry, when the current state is 1 and the next state is 0, the input should be 0, 1. So I have to write it as 0, 1. So understood how to write the inputs for an SR flip-flop? If at all they ask for SR flip-flop. Did you all understand, or should I show for one more? So then do it for SB and RB. Tell me the inputs for SB and RB for the next state. Are you trying? 0x? Okay. Then 0x, 1, 0, 0x. So I'll write here 0x because it is 0, 0, it is 0x. Then it is 0, 1. For 0, 1 it is 1, 0, correct. Next is 1, 1. So it is x0. And next is 1. So you have to compare this and this column. For 1 and 0 it is 0, 1. Next is for 0, 0 it is 0x. Give me all the 8 values together. Let me see. Anybody type all the 8 values together and send? Maybe with a comma, you just type all the 8 values and send. 0, 1. Yeah, 0x, 1, 0, x 0, 0, 1, 0x, 1, 0, x 0, and 0. Good. Harshita Reddy is good. Correct. And Abhishek Pujari for SCA. And okay, you already went to the next column. Huh? Good. 1, 0. I'll not check. I'll just write down 0, 1. It is just the opposite, right? 1, 0, 0, 1. 1, 0, 0, 1. 1, 0, 0, 1. 1, 0, 0, 1. Siddharth Vaishnav, why are you writing single bit? Why are you sending single bit? This is for SCA, correct. Then it is correct. Good. Harshita, correct. Tanushri, send the answer. So because these are changing from 0 to 1 and 1, 0, right? The inputs keep on changing between 1, 0 and 0. Because it is oscillating between only these two states. Here A and A plus are changing alternative. It is just the reverse. It is toggling. So it keeps changing between 1, 0 and 0. So those who have given this answer is correct. So what is the next step? After writing this, what is the next step? Can anybody tell? After writing the inputs, what is the next step? Counter circuit. What, Harshita? Naveen, you are correct. After writing the inputs, first you have to get the equations using the K-map. So after writing the inputs, you have to get the equations through the K-map, right? So I'll go to the next slide. So before that, I'll just clear all this. Oh, the values will also go. So I'll just erase these markings. If I clear everything, I may need these values, so I'm not clearing everything. So here I'll just have the input so that it will be helpful for me to enter here. So now can you put them into the K-map and tell me the equation? I think many of you would have already started doing it. Can you tell the equations? I'll directly write the equations here. Or should I tell you to enter, how to enter it? So first, observe where the variables are placed, right? Observe where the variables are placed. So based on the MSB, your entry should be done. So here you observe MSB is on the, C is MSB, right? MSB on the right hand side and the other two are on the left hand side. So here the values will be like vertically entered 0, 1, 3, 2, 4, 5, 7 and 6, right? So here what is the entry? Oh, I cleared it off. Oh, again it went off. So you only have to tell me what should I enter here for the K-map of RC and SC. What should the entries be? Because I lost the values. It was writing on the screen. When I clear, it all went off. So can you tell what I should enter here for RC? Tell me in this sequence 0, 1, 3, 2, 4, 5, 7, 6. Is type and send? Or you directly tell me the equation, whichever is fine. Either you type and send the inputs or you directly send the equation for SC, RC, RBSB and RASE. Are you all doing it? If you have done for RC, can you tell the equation? Ma'am, please tell to fill the values in K-map. Okay, you just send the input of RC in the sequence from 0 to 7. Send me the values of RC, input for RC in the sequence of 0 to 7. Ankit, will you type and send? Okay, I got it here. No need to worry. I'll do it from here. You can see here. So this is the value for RC. I think this is for SC, I think. SR, right? We wrote it as SR. Just a moment. See, first is S and then is RC. So here first column is SC, second column is RC. Next it is SB, RB and SA, RA. So using this, now I have to enter in the K-map. So this column is for SC and this is for RC. So I'll show it for one of the K-maps, then you can enter. So first is, here you have 0, 0, 0, 1. So this is 0, 1, 2, 3. So how should I enter it? 0, 0, 0, 1. Got it? This is the value for 0, 1. This is for 2 and this is for 3. Right? Then you have x, 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 0. So that I'll fill it as x, x, x and 0. Right? Then I'll show you for RC. This is for, Here the K-map is named as RC. So I should have filled the values for RC, but I'll just change it as SC because I have filled it for SC. I'll just change the name of the map as SC. And here I'll change the name as RC. Right? So you can do however, whichever is convenient. So for SC it is x, 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 0. Then it is 0, 0, 0, 1. Right? So is it right? Have you all done for SC and RC? Yeah. So the equation is C into B dash plus A dash plus ABC. Okay, we'll just check that. So we'll get only one group as a group of single one here. You have only one, right? And here you have a single one. So for RC it is A, B, C dash. And for SC it is A, B, again it is reverse. This is SC is ABC dash and for RC it is ABC. Yeah, RC it is. Please check this because we have changed the K-map names and the sequence. Be careful. First column is SC, second column in the inputs is RC. So likewise, you just show the entries. See here I had written the K-map as, named it as RC, but I had entered for SC. So I changed it for as SC. And this is for RC. But again here in the sequence, this is SC, this is S and this is R. So for S it is A, B, C. A, B, C dash for SC. I'll just erase this and write it again so that it will not be confusing. Right? So for RC it is, see this is the value for RC. So for RC you have a single one here. So what is the value of it? It is A, B, C. And for SC it is, the one is here. So it is A, B, C dash. A, B and C dash. Right? This is for SC and this is for RC. Naveen, can you check again? I think for RC it is ABC and for SC it is ABC dash. But you have given for RC it is ABC dash. For RC it is ABC and for SC it is ABC dash. Because I have changed the namings here. You can observe that I have changed the namings here. By default in the what is that slide it was RC, but I had entered for SC. So I have changed the name as SC. So this is for SC. For SC it is ABC dash. Navin is RC ABC dash. And here I have changed the name as RC. For this it is ABC. Navin, again you send the answers clearly. What is for SC and what is for RC? Someone has written the answer as A, B dash C. No, it is not A, B dash C because see here the row heading is 1, 1. So when it is 1, 1, it is AB only. AB is correct. So the complement will be either for C or for complement will be only for C. Either it will be there or it will not be there. Right? So anyone has done for B, SB and RB? Has anyone done for SB and RB? So this is SB and this is RB, right? So I'll just show the entries for SB and RB. So this is for RB. So I have to enter this column first, right? I have to enter this column. So here it is X001. So this is X001. And next you have X001. Again, it is the same. X001. And then for SB, now I have to write it this SB. So this is the first one I have entered here. This is the second. It is 01 X0. So 01 X0. And then it is 01 X0. Again, it is the same. 01 X0. Right? So now what will be the equations for RB? Has anyone given the equation for RB and SB? RB equal to AB, correct. SB equals to AB dash. So here you have a pair. So RB is AB and SB is AB dash, correct. So your values are correct. RB is AB and SB is B dash, A it is. So you can write it as, sorry, for SB it is A, B dash. Right? So understood? RB is AB, SB is A, B dash. And here, I'll just erase it because it is 1010. For the other one it is. So this part I'll erase now. The inputs. Because I have to enter in the K map. So you'll get at least one question on counter design, that is for sure. You may get either the first one what Shalini ma'am solved using T flip-flop or on the D flip-flop, or such a flip-flop, such a counter using SR flip-flop, or in the lab compulsorily you'll be having this at least as a Viva question for the design of synchronous counter using JK flip-flop. So JK is also very much similar, except that instead of using the SR flip-flop excitation table, we'll be using the JK flip-flop excitation table. Got it? So counter design is a must, whether you ignore chapter module 5 or not, but counter design is a must, at least for the lab, right? And it is, once you know the steps, you don't need to prepare much, right? It is just that you have to know all the steps of execution. So this is, first one is S and the other one is R. So I'll start with 0. So this is 0, 1, 0, 1. Similarly, here it is 0, 1, 0, 1. And here it is 1, 0, 1, 0, 1, 0, 1, 0. So how will be the quads? Just a moment, I'll erase these, the previous values. Yeah. So now RA and SA will be, so this is RA will be a quad here. So C gets automatically eliminated, and here B is also eliminated, only A is constant. So for RA it is A, and here, oh, this side did a mistake here. 1, 0, this should be 1 and this should be 0. So here you get a quad using rolling of maps, right? So this is B, A dash, right? This is A dash. So these are the inputs, correct? SR, RA is A and SA is A dash, right? So all of you got the same answers, right? So now after you got the answers, what is the next step? After you get the equations, what is the next step? By seeing the equations, can you tell what all gates we need? Tell me the next in the chat box, and also what all gates we need. So next step is to draw the logic circuit, correct? So we need AND gate of how many inputs? So first we'll go with C. We'll go with the C state. For RC and SC, what is the gate and with how many inputs? So we need an AND gate with 3 inputs for both R as well as S. Then when we come for B, correct, 3 input AND gates for realizing the C. Then we come for B, when we come for B, AND with 2 inputs. Then for A, AND gate with 2 inputs for RB and SB, correct. Then for A, RA is directly just connect A and SA is directly connect from A dash. So you don't need any gates for the first one. No gate for A, very good. But you have to connect the inputs of A using A and A dash. So we'll see the circuit. So in the next slide, we have to draw the circuit. But I have to have these equations. I'll just check if I have the equations. I have to clear all this. So I'll go for the next slide. Right. So now how will you draw the circuit? For the first one, you just have to connect from R is what? Yes, sir, A or A dash? What is R? So now you only have to give the equations because I cannot get those annotations on the next screen. No gate for A. Okay. What is the input for S? Is S A dash or R A dash? So you have to connect it from A dash is for which one? S, sir? Yes, correct. Okay. So this I have to show it as A dash, or if possible, show the connection. So better not to show because it will get messed up. And for R it is, what is the input for R? A. So for R it is A. So first, before drawing these inputs or writing these inputs, first show the clock signal, right? Show the clock. By seeing the diagram, can you tell what type of clock it is? What type of clock is used for this counter? Can anyone tell? So first, do the clock connections. Very good. It is rising edge. Good. So these are the inputs for the flip-flop A, right? And then for B flip-flop, what are the inputs? So one had AB and the other one had A, B dash, right? So which one for which you have to take? One had the input as AB and the other one had it as AB dash. So R has it as AB and S has it as A and B dash. And connect the outputs of these to the respective inputs. So output of A is for S, output of this gate is for S, and this is for R. Similarly for C, yeah, very good. So you need a 3-input AND gate for R as well as a 3-input AND gate for S also, right? So what are the inputs? For R it is A, B, C, and for S it is A, B, C dash. Then connect the outputs of this. So is the circuit complete now? Or should I show any more connections? Is it complete? Is the circuit completed? Does it end here? Does the solution end here? Or do we have to do anything more? Yes? Hope you are listening to my question. Does the solution complete here? Connect present to next. What is present to next? Gunal. These are the inputs. Where to connect present and next? Gunal, I didn't get you. It is completed. That is all you have to do. You just have to show the inputs like this. If you want to show the connections, then it will be all messed up. See, this B has to be connected here. This A has to be connected here. So don't take that step of showing the connections from these points. Never show it because it will again lead you to a lot of confusion and you may not have the time also in the exam. So better write the gates, mention the names of the inputs and stop it there. Don't show the connections of these inputs, right? Ma'am we should feedback, right? What feedback? Nishant, what feedback? Feedback from where to where? See, this is A is, again, it is a feedback. Ma'am, we have to get the input from output. No, ma'am. Yes, you have to. See, this is A dash, right? This has to be connected like this from A dash. This is what you're asking, right? Now, again, I have to connect A to R. You have to show this. But we need not show it because when we go on connecting like this, see, I'll just show you what happens. If I have to connect B, I'll connect it here. Again, I have to connect it this to A. So I can connect here if you have a A. And then again, this I have to connect it to B. I can connect it here. So if you are able to do it like this, you do. If you are getting confused, no need to do this also. You just show these AND gates and leave it. So the names itself tell that this is a connection from this particular feedback. The names itself tell that they are the feedbacks, right? So from A again, you have to connect it to this point. So if it is A, if you are able to do it, yeah, you will get full marks. If you leave it here also, you'll get the full marks. No need to worry about it. Because if you try to show this, you may end up in confusion and you may be wasting your time. So just stop at this. Even in the textbook, you can see that for the connections where there are too many connections, the connections are stopped at the inputs. Just give the input names and stop it there. So again, this has to be connected to A, right? So this has to be connected to C. So from where will it go to C now? So it leads to a lot of confusion. So better avoid it. So B, I have it here. I can show the connection here. And A, I have it here. I can show it. If you are comfortable, do it. Otherwise, I suggest not to do at all. Because if you start doing this, you'll be wasting your time. Full marks will be given even if you stop it here. As I showed you before, just stop it at that position. Show the gates. The gates are the most important thing here, right? So here you don't have any gates. Here you have AND gate with 2 inputs. Here you have AND gate with 2 inputs, and this is AND with 3 inputs. You have to mention this name of the inputs. This is most important, right? So your marks will not be cut if you don't show these connections. Can you do for SR also? What SR? This is what is SR, right? This is for SR flip-flop only. Nishant, what are you asking? JK, that is what I meant. Yeah, JK example is also there. So that we'll see in the next slide, right? So this is understood, right? All of you have understood this? Okay. What for apologies, Nishant? It's okay, no problem. It happens. What is that? So next is, so after this, you have that example also, JK is also there. So next is you have a slightly different counter here, which is called as loadable counter, right? So loadable counter shown in the following figure has 2 control signals, that is load and count. So here you have 2 control signals. In a loadable counter, you can see this 2 control signals. So here you have those load and count. So first of all, what do you mean by load and what do you mean by count? So load is, suppose we have an input. So what is that register? How many bits of register is this? What is the size of the register? Can you tell? Three. Chandana, why is it 1? Please observe this. If you have a thick line like this, along with a number adjacent to it, this number indicates the number of bits. Please observe now. If there is a thick line like this, along with a number beside it, it indicates that it is a bus. The thick line itself indicates that it is a bus, that is, it has multiple bits, and the number of bits will be mentioned beside the bus. Got it? Chandana, understood? And next, what is load and what is count? So here, what is the type of flip-flop? It is a D flip-flop. So whatever data we give at the input, when it is going to get transferred, this is called as load. If I enter the inputs present at the D to inside the register, it is load. So when load is 1, whatever data is applied at the input will get stored into the register, right? But then what happens if count equals 1? What happens if count equals 1? Then the counter starts to count from this value. So assume that my initial data was 101. So when count is 1, it starts to count. So next count is 110. Next is 111. So after that, after 111, what is the next state? Are you listening? So this counter starts counting from the data present inside the counter. This counter starts counting from the data which is loaded into the counter. Suppose I want to start a counter from 4. I want to start a counter from 4. So what should be the input given? What should be the input given? A load counter or a loadable counter is such a counter where we can start the counting from any required number. Where we can start the counting from any sequence. It need not start from the default sequence, which is 0. So if you don't have a loadable counter, if it is just an up counter, it will just start from 0, 0, 0 and it will count till 1, 1, 1, right? This is for a normal counter. Whereas for a loadable counter, if I want to count from 3, if I want the count to start from 3, then at the D input, I have to give the input as 3. So this will get loaded inside the register when LD equals 1 and CT equals 0. When load is 1 and count is 0, I will put my data into the, or load my data into the D register, into the 3-bit register, right? And then I'll make load as 0 and count as 1. Then I'll make load as 0 and count as 1. Then what happens? It will start counting. So the first count will be 3, next count will be 4, next count will be 5. Like this, it goes on counting. Understood? So did you all understand what is a loadable counter? Yes or no? Did you all understand what is a loadable counter? So here you have a no, ma'am. So where is your confusion? Can I know, Manoj? I'll just clear all this. See, in the normal counter, in the previous counter, it was a up counter, right? Up counter or down counter. We don't specify from where it has to start. See, this is the first state. In this counter, the first state is 0, 0, 0. Next count is 1. Next is 2, 3, 4, like this. It keeps on counting from 0 to 7. So by default, it will start with 0. You won't have to give any data there, right? See, in this counters, you won't give any data input, right? We'll go to the T flip-flop. So you'll just give a 1 here, and again it will start with 0. You don't have any data input here. It will just start with a 0. So the first count will be by default 0, 0, 0. Whereas here in the loadable counter, you can start from any required number. So I suppose I want the counter to count from 5. Suppose I want the count to begin from 5. So here I have to load the data as 101. 101 is what? It is the binary for 5, right? So here at this position, I'll give the input as 101 and I'll make load as 1. So this will be made as 1 and count will be made as 0. So when load is 1 and whatever input you give here, that will be stored into the register. When load is 1 and count is 0, whatever input you give here, that will be stored or loaded inside the register. After that, we'll make load as 0 and count as 1. So now what happens? Can anyone tell what happens now? What do you mean by 1015? See, I have given the input here, right? This is nothing but the binary value of the decimal number 5. 101 is nothing but the decimal value of 5. I just wrote a 5 here to make you understand that this is nothing but it is the binary for the decimal number 5. Right? Okay. So I want the counter to start from the count 5. I don't want the previous counts. I just want it to start from 5 only. So at that situation, I'll be using a loadable counter. Whenever I want the counter to start from a different number, instead of the default count 0, 0, 0, then I'll use a loadable counter. Yes, Gunal, is it not sequential then? Of course it is sequential. It is sequential, but the beginning number, the initial value, the first value can be set. You can set the first value, but it is sequential. So after 5, what is the next count? Can you tell now? After 5, what is the next count? Or what are the counts? The first count is 1, 0, 1. What is the next count? 6. What is the binary for 6? You have to be thorough with this. 1, 1, 0. Next is 7. After 7? After 7? Correct. It is 0, 0, 0. Then 0, 0, 1. 0, 1, 0. 0, 1, 1. Like this, it goes on repeating the sequence. Right? So this is the sequence. But here you are going to set only the beginning value. This is done only by the loadable counter. So here the same thing, whatever I explained here, till that is there in this table. This is the state table. So when clear and here you have the clear and signal, the additional signal to clear the data. Suppose I want to set with a different data, then I will be clearing this using clear n, right? When clear n is operating, whatever load or counters, it is not considered. So all the next states will be 0. And then when clear n is high, here clear n is an active low signal. So when it is 0, clear operation will be performed. And next, when load is 1, irrespective of count, the next count will be generated. And when load is 0 and count is 0, it will not change. The count will not change. It will be the same, right? Then when load is 0 and count is 1, then the count will be present state plus 1. So whenever load is 0 and count is 1, the next count will be counted. The next number will be displayed. When both are 1, 1, here it is 0, 1 and x. When it is 1, 0, it will load the data from the input to the register. When it is 1, 1 also, even though count is 1, count will be overridden. So you can see here, when both load and count are 1, load overrides count and data is loaded into the counter. Whether irrespective of count, whether it is 0 or 1, if at all load is 1, whatever data I've given at the input will be stored into the register. Understood? So this is the loadable counter block diagram, and this is the summary of the operation of the loadable counter. Right? So we'll go for the next one. Next is counter for other sequences. So here I'll just tell you about this. This you can try by yourself. Yeah. So here I'll just explain about this. You can write this. So after this, the further steps will be the same, right? You just try out these problems. The solutions are given. If you're not getting it same, then we'll do it in the next session, tomorrow's session. Counter for other sequence. So what do you mean by other sequence? So here previously we saw counter for beginning with a different number, to start with a different number. That was using loadable counter. Whereas here you have for a different sequence. It will not be in the same sequence, but again it will be in a ascending order only. So the order also need not be considered here. You'll have it in a different order as well as different sequence. So nothing will be followed. It is just a random counter. So here, this is the sequence. This will be the question. It will be given in the form of this state graph, or it will be given in the form of number. It will be given in the form of number like this 0, 0, 0, 1, 0, 0, 1, 1, 1. So it will be just given in the form of a sequence. So present state will be writing as the previous tables from 0 to 7. And here, please observe here, when you want to write the next state, you have to refer the state graph and then only write the next state, right? So after 0, what is the next state here? Refer the graph and then write the next state. After 0, what is the next state? It is 1, 0, 0 here. So you have to enter it as 1, 0, 0. And here present state is 0, 0, 1. What should be the next state for 0, 0, 1? Here you don't have. In this particular sequence, you don't have 0, 0, 1. So this next state will be hyphen. You don't have the next state for 0, 0, 1. Next, 2. So you have 0, 1, 0. So you have that in this sequence. So what you should do, you have to check what is the next state after 2. So what is the next state? It is 0, 1, 1. So enter 0, 1, 1. Right? And then present state is 0, 1, 1. So after 0, 1, 1, what is the next state? Observe that in the state graph. So that is 0, 0, 0. So you'll be entering the 0, 0, 0. Right? Then you have 1, 0, 0 as the present state. So for 1, 0, 0, what is the next state? Next state is 1, 1, 1. So you have to write it as 1, 1, 1. And next here you have 1, 0, 1. So try to find 1, 0, 1. You don't have a 1, 0, 1 here. So you will not have a next state for a state which is not present in the state graph. Then you have 1, 1, 0 here in the present state. Do you have a 1, 1, 0 in the state graph? You don't have a 1, 1, 0. So you have to write the next state as unknown. So whichever is unknown, show it as hyphen, right? Then for 1, 1, 1, the next state is 0, 1, 0. For 1, 1, 1, the next state is 0, 1, 0. So you write it as 0, 1, 0, right? So after entering this, next you just have to write the inputs using the excitation table. So I think further you can write. This is the only difference. And here you just enter this because here you have to write don't care for this unknown next state. Wherever you have the next state as unknown, fill those rows directly with don't cares. So these rows will be filled with don't cares. Whichever row doesn't have the next state, just fill them as don't cares. Now fill the rest using the excitation table. So for TC, it has to toggle. So the input will be 1. This is 0, 0, 0, and this is 1. So write the inputs like this. Then again put them into the K-maps, find the equation, and draw the circuit. Right? All the other steps remain same, except that when you write the next state, you have to refer the state graph. Right? Refer the state graph for the next state. Compare with the present state. Check for the present state in the state graph. Whatever it is leading to the next state, write that in the next state. So if a state is not present in the state graph, for that state, the next state will be written as unknown. So for that, the inputs will be don't care. Understood? Today we will upload Johnson counter is only there in the syllabus. Even ring counter is not actually included in the syllabus, but we don't know. When the question paper is set, because Johnson counter is there, sometimes by default they assume ring counter is also there and they may give that question also. So better, it is just one small difference, right? Better prepare for both. Yeah, this will be done today. So understood? Counter for other sequence. So shall I go for the next one? So I'll just clear all this. So for that, the equations, you have to write the inputs, but the rest is done here. The equations are derived using the K-maps, and the circuit is also written for this counter, which is the other sequence. So only this you have to fill and verify your answers. Then you have the equations also and the circuit also. See here, the circuit is written only with the inputs. The connections need not be shown, right? And next is, yeah. So in this other state counter for other state, other sequence, you just have to note that in the above problem, initially when the power is switched on, suppose the counter was switched off for some reason, and if the power is switched on, if at all the circuit enters to an invalid state. Which are the invalid states here? The invalid states are 1, 5 and 6. So if at all it enters to 5, then what is the next state? Next state is unknown. So will it count further? If at all the counter on, power on, when I switch on the counter, and if the default count goes to 5, 1 or 6, will it start counting? Will it go to the next count? Can anyone answer? Will it count the next one, next count? No. Why does it not count? Because it don't know. Suppose the default initial state is 0, 0, 1. What is the next state? We have not given here, right? It is don't care. So it will not count. So to avoid that, what we should do is to avoid that or to overcome that issue, which is called as lock-in condition. So you can see here, it is called as lock-in condition, right? So when the counter goes to a invalid state, it is called as lock-in condition. So to come out of this or to overcome this problem, whichever states are invalid, those will be mapped to one particular state. So if the counter goes to 110, then the next state should be written as 111. If the counter goes to 001, next state should be written as 111. And even if it is 101, next state should be written as 11. Either you can write this as the next state or 0 as the next state, right? So this is called as self-correcting counter. So this particular solution is called as self-correcting counter. Understood? Okay. So we'll see the next one. So next is, so JK, someone had asked for JK, right? So it is here for the same thing, others counter for other sequence only. It is shown with a JK flip-flop, right? I'll just tell the details, explain it for only one input, that is JC and KC, then rest remain the same. So now you know how to write present state and next state, right? You all know how to write the present state and next state. It doesn't have an idea. Yeah, because it doesn't have an idea, it will not go for the next state. So here you have to again do the same exercise, compare the inputs, the present state and the next state, and write the inputs. So we'll do for JC and KC. I will explain only for JC and KC. So now observe C and C plus. So what is the input for present state is 0, next state is 1. So here present state is 0, next state is 1. And what is the inputs? J and K should be 1 and X. Hence here you have 1 and X, right? And next is 0 and unknown means just fill it as XXX. So wherever you have this unknown, just fill those rows as don't care. And next is 0 and a 0. So if it has to remain at 0, what are the inputs? It is 0, X. So we'll be writing it as 0 and X. So next is also 0, 0. So input will be 0, X. And next is, again here it is 1, 1. So for 1, 1 it is X, 0. So you have to use the excitation table of JK flip-flop and fill the inputs. So once you fill the inputs, again the further steps are same. Put each input, I'll just show in the next slide. Put each input in a different K-map and solve for the equations. So you can see here that for each input, this is for JCKC, you have to put it for in a separate K-map and derive the equation. This is for JBKB and this is for JAK. Once you get the equations, again the same procedure, draw the circuit with the gates and show the inputs at the gates, right? So everything is there except that you have to refer the excitation table of the JK flip-flop. So next you have sequential parity checker. You have another 2-3 topics, state tables and state graphs. So many are there. So it will take another 15 to 20 minutes. Hope I can continue, or should we postpone to tomorrow? It will take another 20 minutes for sure. Continue. Okay. Yeah, it is just 4. Okay, we can wind up by 4:30. So next is parity checker. Okay, what is parity? What are the types of parity? Can you tell? If you know the parity, then this is very simple. Okay, I'm doing. Swati, you are the only asking for tomorrow, but all of them, others are asking for today only. So we'll finish off another 20 minutes. So the types of parity is odd parity and even parity. But what is odd parity and even parity? Anybody doesn't know what is odd parity and even parity? Okay, Swati. Yes, should I tell what is odd parity and even parity? So suppose there is a data, a binary data. I'll just take the example from here only, or I'll write it separately. 1 0 1 1 0 1. So here count the number of ones in this particular data. How many number of ones are there? You have 5 bits of ones, right? Similarly, here how many bits of ones are there? 2 bits of ones. So when we count the number of ones, and if the count is an even number, it is called as even parity, right? If the count of number of ones in a given data is even, then it is even parity. If the count of number of ones in a given data is odd, what is 5? 5 is an odd number, right? Hence this has odd parity. So parity is nothing but it is count of number of ones. So in that parity you have 2 types, odd parity and even parity. So if the count is an odd number, then it is odd parity. If the count is an even number, then it is even parity. Right? Understood, right? So why we need a parity checker? So first you have to know what is parity. So I have told what is parity. Next we have to see what is parity checker. So when binary data is transmitted or stored, an extra bit called parity bit is added for error detection. So this is the function of a parity checker. Parity checker is mainly used to detect if there are any errors in the received data or the data that is stored. Got it? A parity checker is used for error detection. The main purpose of parity checker is to check if there are any errors. So how is it checked? So we'll see here. So you have an example here. If the data is transmitted in group of 7 bits, assume that you have a group of 7 bits. So this is the data which is transmitted in a group of 7 bits. This is the data which is transmitted. An 8th bit can be added. So you'll be adding an 8th bit to it. So this is the 8th bit. So here it is written, this is the data of 7 bits. And for that, you are adding a 8th bit. So what type of 8th bit? An 8th bit can be added to each group of 7 bits to make the total number of ones as odd parity. an 8th bit can be added. So this is the 8th bit which can be added such that it can make a odd parity. So what is it? Finally, we want all the data to have odd parity. We need all the data to have odd parity. So what we'll do is, to a group of 7 bits, we'll add an 8th bit which makes the parity to be odd parity. Right? The 8th bit is added such that the parity should be odd parity. See here in this 7 bits, there is no 1. If the number of ones is 0, then it is even parity. Please remember this. If the number of ones is 0, then it is even parity. If the number of ones are 0, some assume that it is odd parity. It is not odd parity. It is always even parity. Right? So when it is even, we want it to be odd parity. So we'll include a 1 here. So totally it becomes now 7 bits of 0 and 1 bit of 1. So now we have only a single bit of 1. So this makes the data to be a odd parity data. Got it? And in the next data, in the next group of 7 bits, you have a single bit here. So already it has an odd parity. So we will be adding a 0. So that we will not change the parity of the data. So data should have only odd parity. That is our requirement. So we'll add the 8th bit such that it gives a odd parity. Already the data has odd parity, so we'll add it as a 0. In the next group, it is 0, 1, 1, 0, where you have 4 bits of 1. So 4 bits of 1 means it is even parity. So we'll add the 8 bit as a 1. So now it becomes 5 bits of 1. So this makes a odd parity. So similarly, we'll be adding the 8th bit such that it makes the parity to be odd. Understood this? Did you all understand this? How to make it as odd parity? Any doubt here? To make it odd parity. Okay. So we'll go for the next one. Right? So first, we are generating a data that will have only odd parity. This is not the checker. This is only the data. We are giving the parity bits. We are adding the parity bits. It is just the initial stage. It is not the checker. It is a generator. This is the parity generator. So here, this data is shown for parity generator. What type of parity generator? It is a odd parity generator. So this is for odd parity generator. It is not a checker. So checker we have to see in the next slide, right? So next is a sequential circuit which has one input. A parity checker is designed for serial data. So the circuit is as shown below. So you have a circuit here. The parity checker is designed for serial data, means the data will be coming in a sequence of bits, right? It will be coming in the form of one after the other. When a sequence of ones and zeros is applied to the X inputs, this is the X input. So here it will be giving the data input. The output should be Z equals 1. Output should be always 1. Why should it be 1? And one more thing I have to tell is odd parity is always represented with 1. Odd parity is always represented with 1 and even parity is always represented with a 0. So if the parity bit is high, that means the data has a odd parity. If the parity bit is 0, then the data has a even parity, right? So here you are inputting a stream of data where Q is output and Z should be always 1 because it has to check that the parity is always odd parity, right? So if the received sequence has odd parity, if at all the Z becomes 0, that means the received sequence does not have odd parity. So this is a parity checker. Whereas previously what we saw, that was parity generator, and this is a parity checker. So thus, if data with odd parity is transmitted to the circuit, an output of 0 indicates that an error has occurred in the transmission. So we always assume that the parity should be odd, because if there is no error, we assume that Z is always 1. If at all Z becomes 0, that means the parity has changed to even. That means whatever received data has a error. There has some error has occurred in the transmission medium. Because of that, the parity has been changed to even. So if there is no error, that means the data should have a odd parity. If there is an error, even if one bit is changed, then there would be an error. Even if one bit of 0 is changed to 1, then the parity will change to even parity, right? If the parity is changed, we can detect whether there was an error or there was no error. Next, the clock input is necessary to distinguish the consecutive zeros and ones. So we have a clock input. The purpose of clock is to differentiate between the adjacent zeros and ones. The following figure shows the output waveform for the circuit. So this circuit is represented with the output waveforms. This is the stream of data entering. X is the stream of input data. So clock signal to differentiate between the ones and output. So again you get a 1. So now again it goes to high. So for the first odd bit, the output goes to 0. So if the next one bit comes, it becomes even, so it goes to 0. So if one more high bit comes, it becomes high. So whenever an odd number of 1 is detected by the output will be high. So here the fourth bit of 1 is occurring, so the parity is even, so it goes to 0. Got it? So this is the timing diagram for this parity checker circuit. So understood this parity checker? Any doubt here? Ma'am, I didn't get parity bits. Manoj. In the parity generator in the previous slide or this slide? Manoj, are you asking in the previous slide or this slide? Previous slide. Okay. Say I want the parity of some data to be always odd parity. What do you mean by odd parity? I'll show you for 4 bits. So now what is the parity for this 4 bits? I have 0, 0, 0, 0. What is the parity for this? Parity. It should be in terms of odd or even. So it is even. Don't tell in terms of 0 or 1. Tell it to be more specific, tell it as even or odd. So for this, the parity is even. But I want it to be always odd parity. So what I should do if I want an odd parity? What is the bit that I should add now? It is okay if I had a 5th bit. I have to add a 5th bit such that the parity of this whole number becomes odd parity. I have to add a 5th bit such that the parity of this whole 5 bits becomes odd parity. So I have to add a 1. Got it? Now, what is the parity of this data? 0, 1, 0, 0. What is the parity of these 4 bits? Odd. So what should be the bit I had now? 0. So the parity should always remain as odd parity. That is our requirement. Understood now, Manoj? The same thing in the previous slide, it is shown for 7 bits of data. Initially, the first data was 7 zeros. So it was having an even parity, so we had to add a 1. So suppose in the next bit, next data, it is 0, 1, 0, 0, 0. What is the parity of this? This is odd. So what should be the bit we add? 0, right? So understood now? Manoj, is your doubt cleared? Yes, ma'am. Okay, thank you. So now this is about the parity checker. So we'll go for the next one. Next is state tables and state graphs. So state tables are the ones which we use for designing the counter, and state graphs are the state diagrams which we use to indicate the sequence. This is nothing but the state graph, and this is nothing but the state table, the present state, the next state. So these are the state graphs and the state tables. So what do we have here? The state tables and the state graphs provides a systematic approach used for analysis of larger circuits, right? So when we analyze larger circuits, we need this state tables and state graphs so that we can systematically solve the problems. Then the state table specifies the next state and the output of a sequential circuit and the present state with the input, right? So this is all we know. We have already done in the counter design. So this is the steps to be followed while constructing a state table. This also you know, right? Determine the flip-flop input equations and the output equations from the circuit. Then derive the next state equation. Then plot the next state map for each flip-flop. Just a second. This is for if a circuit is given. How will you design the state tables and state graphs when a circuit is given? Previously for the counter, design the circuit. Whereas these are for if a circuit is given. Suppose this circuit is given, you have to design the inputs. You have to design the inputs, right? The circuit is given, so that for this circuit you have to give the inputs. Whereas initially in the counters, we had a sequence, right? We had a sequence, we knew the output, then we had to find the inputs and find the circuit. But here we have the circuit. Using that, we have to find the equations, then we have to write the inputs, then find the outputs. So this is just the reverse of the counter design. So what is the first step here? The state table specifies the next state and output of a sequential circuit in terms of present state and input. Then the following steps can be used to construct the state table. Suppose you are given a circuit and when you want to construct a state table. So it is the reverse of a counter design. So please note this when we have to construct the state table. So for that, from a circuit, so that I have not given here, from a given, for a given circuit, you can take it down as for a given circuit, when you have to construct the state tables, what are the steps? So these are the steps for that. Determine the flip-flop input equations and the output equations. That is, by seeing the circuit diagram, you have to determine the flip-flop input equations and the output equations. Then derive the next state equation for each flip-flop from its characteristic equation, right? By using the characteristic equation, derive the next state equation and then plot the next state map for each flip-flop. So please, these are the differences, right? In the counter design, you'll be using excitation table. For the counter design, you'll be using excitation table. Whereas for determining the state tables, you'll be using characteristic equation. And then you'll be plotting the next state in the map for each flip-flop, right? In the map, you'll be plotting the next state. Whereas for counter design, you used to plot the inputs, right? You used to plot the inputs, but here you have to plot the next state. Then combine these maps to form the state table. Combine these maps to form the state table. So a state table which gives the next state of the flip-flops as a function of their present state and the inputs is referred to as the transition table. So here the state table is called as transition table. Got it? So as of now, such a question has not occurred, but these are the steps. You can just be aware of the steps. So I'll just briefly explain the next slide. Because this is a very new topic which is added only for your syllabus. So I can't tell you that they won't ask also, because it is a new topic. It has not been asked in the previous question papers, right? So for that, you should know two models, the Moore model and Mealy model. So you have two models here. This is used for the generation of state tables and state graphs. Moore model and Mealy model. So Moore model is the one which, so if the output of a sequential circuit depends only on the present state. This is the most important thing. When the output of a sequential circuit depends only on the present state of the flip-flop, such a sequential circuit is called as Moore model. Understood? If the output depends only on the present state, it is called as Moore model. Whereas, if the output of a sequential circuit depends on both the present state of the flip-flop and the inputs, if the output depends on both present state as well as inputs, it is called as the Mealy model. Understood the difference? In Moore model, it depends only on the present state. Whereas in Mealy model, it depends both on the present state and the inputs. It depends on the present state and the inputs. This is Mealy model. So depending on this, you have to create the state tables. So you have an example here. Derive the state table for the following circuit. And the circuit given is Moore model. So this circuit will be your question. For this circuit, you have to derive the state table. So here it is called as transition table, right? So for that, what was the first step? First step was to determine the input and output equations. First step for determining the state table is, you can see here it is, determine the flip-flop input equations and the output equation. So again, here it is given here. The flip-flop input and output equations are. So how do you write this? You have to observe the inputs here. At the input of DA, what is the gate? You have a XOR gate, right? So observing the gates and the connections, you have to write this equations. So if you see here at DA, you have a XOR gate. And what are the inputs for that? You have X and B dash as the inputs. So hence, you have X and B dash. What is the type of gate? It is a XOR gate. So X mod B dash. So mod is always nothing but XOR, right? Mod means it is XOR. So X XOR of B dash is the input for DA. How is it B dash? If it is not mentioned here, then you have to trace the connection from where it is given. So it is B dash. So this is for DA. Then what is DB? For DB it is X OR of A, because you have an OR gate here. Hence it is either you can write it as XOR A or X plus A. And you have to write the equation for the output also, right? You have to write the equation for the output also. The Z is the output. These two are DA and DB are the inputs for the flip-flop, and Z is the output of the circuit. So what is the equation for the Z? For Z you have a XOR gate whose inputs are B and A. Hence it is written as A mod B, or it is A XOR B. You can write either as A XOR B, or you can write it as A mod B. So did you all understand this? How to write the input and output equations? A and B dash. Very good. So for the next one, you are telling, right? For DA, yeah. So hope you all understood how to write the input and output equations, right? So next is the next state equations. Second step is to write the next state equations for the flip-flops. That is A plus and B plus. How will the next state be operated? So what is A plus now? So what is the next state? How is A dependent here? What is the input for this? For this it is A is nothing but it is generating from D. If it is a D flip-flop, output will be same as input. So it is A plus is nothing but same as the input. So write it as X mod B dash. Similarly, B plus. So whatever is the input for DB, same thing will be the output. Sorry, this is B. Whatever is the input at B, same thing will be the output. So whatever is here, same thing you have to write. So you'll not write the next state equations for the output. You'll be writing it only for the outputs of the flip-flop. Only at the outputs of the flip-flop will have the next state, not for this. Right? So understood this? Next is to write the corresponding maps as shown below. So using this, you have to write the corresponding maps. So this is for A plus and this is for B plus. For A plus, for 0, 0, 0, it is X mod B dash. What is X? X is 0. So you have to substitute the values for X. X equals 0 and B dash is, what is B? B dash is 0 here. So if it is 0, what will be the value? When I apply XOR gate, if both are 0, the output will be 1. Hence it is 1 here. So you have to put the values for these for each entry and then do this entries. You will not be finding it anywhere else, right? You have to put the values of XAB into this and then solve it for XOR, then only you'll get this entries. I'll just check the chat box, there's some doubt. Ma'am, circuit diagram, they will only give and should we write the equations? Yes, yes Manoj, circuit diagram is the question, part of the question. They'll give the circuit diagram and for the given diagram, you have to write the input and output equations by seeing the circuit, right? So I'll just clear all this. Yeah. So now how to write this? I'll just explain once again for A plus. See, this is for A plus, right? So for A plus, what is the equation? It is X mod B dash. So what is X mod B dash for the first entry? So here, what is the value? Values you have to consider from here. When it is, this is A, this is B, and this is X. So the equation is X mod of B dash. What is the value of X here? It is 0. Value of B dash, here B is 0, so B dash will be 1. So 0 XOR 1 is, sorry, this is 0 because here it is 1, complement of that is 0. Hence it becomes a 1. Sorry, I think I am making a mistake. 1 second. First, the value of X is 0, value of B is also 0 here. So complement of this is 1. So this is 1. So the entry will be 1. So XOR of 0 and 1 is 1. So for an XOR gate, if the inputs are same, the output is 1. And if the input is different, output is 0. So this you have to remember. For 1, 1 also the output is 1. When inputs are different, the output is 0. When inputs are same, the output is 1. Hope I am right. Or am I telling the reverse? Can you recollect? Can anyone recollect the truth table for XOR gate? Reverse, huh? It is reverse now. Okay, thank you. Yeah, that is what I felt. Because XOR gate we use for parity, and this is, here it is 1, 1, and here it is 0, 0. But then here the entry is 1. How did we get a 1? Yeah. So when it is different, it is 0 mod 1, right? So it is 1. Yeah, here I have written correct, but here while writing the truth table, I made a mistake. Okay, when the inputs are different, when the values are different, the output is 1. Similarly for the next. So here B is 1, so it is 0 mod 0 XOR. So what is the complement of 1? So it is 0. So here it is 0. So hence the entry is 0. And next B is 1 here, so B dash will be 0. Again it is 0 mod of 0, so it is 0. Right? This is also 0. Here it is 1, so it is 0 XOR of 1. So the entry will be 1. So understood how to do the entries? Should I continue? Should I tell for all the entries? 1 0 0 0. What is this, Naveen? No need, ma'am. Preeti wants me to continue. So I'll just show for 1 or 2. I mean, what is this 1 0 0? Okay, it's by mistake. So here I'll just show for this entry. So here, what is the value of B? B is 0. B dash will be 1. And here it is 1. So when X is 1 and B dash is also 1, what will be the output? What will be the result? It will be a 0, right? So hence, for this cell also it is 0. Similarly here, X is 1 and here B becomes 0. So when X is 1 and B is 0, it will result in a 1. And here B is a 0, X is a 1. So it is 1 0. So this also becomes 1. Got it? Preeti, did you understand or should I show again? Preeti understood? Who asked me? Preeti only, right? No, ma'am, got it. Okay. One second, I'll just clear all this. So I'll just show for this. I'll put the equation. See here, the equation for A plus. Or shall I show for B plus now? Because A plus we have already done. I'll show for B plus, right? For B plus, what is the equation? It is X plus A. This is simple. So this equation is simple. It is just the OR gate. X plus A. So here, what is the value of X? X is 0. So it is 0. Plus A. What is A? A is also 0. So you have to check the headings of each of the cells, right? This you have to check. These will be the values for your X and A. This you have to remember. How will you get the values of X and A? You have to check the headings of the cells. Similarly here, how will you get the values of X and B? Depending on the cell headings, that is whatever you have given the names. Those will be the values for the variables, right? So now what is the result here? Here it is 0 plus, what is A? A is also 0. So result is a 0. So entry is also 0. Now for this, what is A? A is 0. X is also 0. Hence result is also 0. Hence the entry is also 0. Got it? Here A is 1, but X is 0. So what is 0 plus 1? It is a 1. Then here again A is 1, X is 0. So this is also 1. Understood now? See here X is 1. When X is 1, irrespective of whatever is A, whether A is 1 or 0, the result will be a 1. So all the bits are 1s. Understood? Yes, ma'am. Siddharth, understood? Okay. So this is to generate the equations. This is the second step. That is, the next state equations for the flip-flops are generated using this step. And after that, you have to now write the transition table. This is called as the transition table. So for that, how will you do? State tables, but when we do it from the circuit to the state table, it is called as transition. Combining these maps is the transition table A. This is the transition table A. So how to combine them? Which gives the next state of both the flip-flops A plus comma B plus as a function of the present state and input. So A plus and B plus is given as the function of present state and the input, because here we have considered the inputs also, right? X is the input and A, B are the outputs. So together we have got the equations. So for A plus, the states are written like this, and this is X. In this example, the output depends only on the present state of the flip-flop because it is a Murray model. You have to observe what is the model given there. It is a Murray model. In Murray model, the output depends only on the present state and not on the input. So a single output column is required. So this is the output column which is with the only present state, right? So here you have AB. AB is the present state. This is A plus B plus, which is the next state. For next state, you should have the equations. What is the next state equation? A plus B plus, and here you should have derived the equation here. For A plus, you have to group it and get the equation. You have to form the groups and get the equation. Here you'll have two pairs, and here you have a quad, two quads. So here you have two pairs. Here you have two quads. So for A plus, what is the equation? A plus equals, this is B bar X bar, B bar X bar. And this is A X. This is AX and this is B bar X bar. A plus is B bar X bar. Hope I am correct. And B bar X bar plus, you have one more here. You have it for X BX. You have it as BX. For this pair it is B bar X bar, and for this pair it is BX, right? For here it is A plus X. For this second it is A plus X. This is for B plus. Right? So these equations, you just type in the chat box. I'll just remove it. Did you all get the equations? Yes, ma'am. XB plus X bar B bar, B plus equals A plus X. Very good. It's already here. So I can clear this. Okay. So now I'll move to the next slide. So here, combine this. So using those equations, you have to get the X equals 0 and X equals, when X equals 0 and X equals 1, you have to get these values. So AB is the present state and this is the next state. So let me write the equations here. So here I'll write it as, for A plus it is XB plus X bar B bar, and for B plus it is X plus A, right? These are the equations. Next. So now when X equals 0, so here for both X is 0 and here X is 1. When input is 0 and when input is 1. So what will be the next state? Here it is A is 0. So for 1, I'll just show you A plus This is A plus and this is B plus. This is A plus and this is B plus. So here for the first option, we'll take this as for A plus, we have to consider xb plus x dash b dash. So x is 0. What is b here? B is also 0 plus x dash is 1, b dash is 1. So here it is 0 plus 1. So the result will be 0. It is 1 here. So you have a 1 here. This is for A plus. And this you have to check for B plus. So for B plus, what is the value? X is 0. And what is A? A is a 0. So it is 0 plus 0. Hence, this is 0. So I'll show you for the next value. For this, I'll show you once so that you can understand better. So this is the last, I feel. Where is it? Clear on the drawings. So now we'll check for the second state, right? We'll check for this. So for A plus it is, again I have to write down the equation. It is, what is the equation? I forgot. xb plus x bar b bar. So this is xb plus x bar b bar. This is for A plus. So first column is for A plus, this column is for B plus. For each value here, you have to check one value. For this, the equation will be xb plus x bar b bar. Whereas for this, the equation will be x plus b. If you want to get this value, you have to do x plus b. If you want to get this value, you have to do xb plus x bar b bar. Understood now? So for the second row, we'll check. X is 0, B is a 1 here, plus X bar is 1, B bar is 0. So what is it? 0 plus 0. Hence you got a 0 for A plus. And then for B plus, it is X plus B. So X is 0. And what is B here? B is 1. For B plus it is x plus A, sorry, it is x plus A. This is wrong. It is x plus A. So what is A here? A is 0. Hence, you get the result as 0. So this is 0. Got it? So like this, for each value, you have to derive it or calculate it through the equations of B plus A plus. The first bit is A plus here, and the second bit is B plus. This you will be doing when x equals 0. And for this, again, you have to implement those or calculate this using the equations. That is, you have to put x as 1 for this. And here you are putting x as 0. Understood? So this, you can just verify it. The solution is here. So after getting this table, after getting this transition table, you have one more table here, which is in terms of S. So here, these values, right? These values are just given a name. See, this is named as S0, this is named as S1, this is named as S2, and this is named as S3. So based on this, you'll be just writing these in the forms of S1, S0, S1, S2, S3. See here, what is the value of this? This is S3. Right? Hence it is S3 here. Here you don't follow the binary code. You just name it in a sequence. You don't follow the binary. 0 means it need not be always 0, 0. Here 2 means it need not be 1, 0. This value, the bit is not the binary value of this subscript. Please note that. Right? Here it is S2, but this need not be the binary for 2 in this particular problem only. Right? So however it is here, we'll just name them in a sequence as S0, S1, S2, and S3. Then whatever we have named here, the present state, based on that, we'll be writing this next state as S, representing with the state. So here it is S3, I mean S3, this is S0, this is S1, and this is S2. Hence it is written as S0, S1, S2. And this is written as S1. These both are same, which is S2. So it is S2 here. Again, this is 0, 1, which is nothing but S1. Hence this is S1. So understood? The next state, then the output. So this is the state tables. And still, after writing the state tables, you have to write the state graph. So state graph, I'll just show you. So for writing the state graph, we need this representation using yes. So this is the state graph. So in our state transition diagram for the flip-flops, we had only 2 states, right? That is 0 and 1. But here we have 4 states because we had 2 flip-flops, right? So those 2 flip-flops have been summarized as yes. So based on this next state, see S0 will have the next state as S3 or S1. I'll just show you. So this is S0. S3 can lead to S1 or S3. So basically you just write down the states, whatever states are available for this particular circuit, write down the state. You have S0, S1, S2 and S3, right? These are the states. So now if I compare with the state table, S0 leads to S3 and S1. For S1, the next state is S0 or S2. So these you have to show in terms of the graph. So S0 is leading to S3 or S1. And S1 will lead to S0, S2. So the arrow mark points from which state to which state. See S0, from S0 it goes to S1. From S0 it goes to S3. So the arrow marks are pointed towards the destination state. Got it? And these are the values written on the arrow marks are the values of X. See here S3 is 0 and here S1 is 1. So S3 is 0 here, S1 is 1. This is the value of the X. Whatever you write here beside the arrow mark is the value of X. So this 0, this is the value here. Now what was the value of this? This was 0. Hence it is written as 0. This is Z. This is the value of Z, I think. Just a moment. Yeah. So here the output you are mentioning below the state. See S1, S0 is 0. S1 leads to 1. S2 leads to 0. S3 leads to 1. So this is the value of the Z. 0, 1, 0, 1. So whatever you have in the denominator, those are the values of the Z. Right? So understood this state graph? So this completes the solution for this state tables and state graph. Okay. Y, Z value is 0, 1, 0. That is depending on the Z equation output. We have initially written the equation for the Z, right? What is the equation for the Z? A mod B. So that you have to calculate. Here when you are writing this, you have to calculate A mod B and then write the value. A XOR B. So this equation we have already derived based on the circuit. Got it? Based on the circuit, we have already derived that equation and then it is written as A XOR B. Manoj, understood? Got your answer? Manoj? No, ma'am. Didn't get a. Wait. See here. One second. In the equation, in the circuit, you have a gate for the Z. What is this gate? This is the XOR gate. So whatever is the Z arriving from, Z is arriving from this XOR gate. And for the XOR gate, the input is B and here you have A. Right? Hence, you have written the output for Z as, so Z equals A XOR B. So this is based on the circuit given here. This is Z. From where is it coming? From the XOR gate whose inputs are B and A. Hence Z equals A XOR B. So this equation is used to write the values of Z. Using that equation, I'll just write that equation here again. So here Z equals A XOR B. So what is the value of A here? A, it is 0, 0. Right? When the input is same, the output will be 0. When the input is different, output will be 1. When A is 0 and B is 0, the result is 0. 0 XOR 0 is 0. 0 XOR 1 is 1. Next you have 1, 1. So for 1, 1 again, the output is 0 using an XOR gate. And here you have 1, 0, so it is 1. I think now you would have understood. Right? Got it now, Manoj? Yes, ma'am. Okay. So any other doubts? So this is the state graph and next questions. So we'll upload the questions. So almost all the questions have been covered in whatever examples we have done today. Go through the questions. If at all you feel any of the solution for any question is not discussed today, you can ask in the tomorrow's session, right? So okay, now it's already time. So we shall wind up now, right? So we'll wind up now. If you feel any questions are not discussed today, you just ask it as a doubt tomorrow, right? So tomorrow we'll have for module 1. I have not done it in the offline classes also. And that is quite easy because you'll not go wrong in the module 1 for any calculations. You don't have much calculations in that. So please all of you attend tomorrow, right? So tomorrow is module 1, that is analog electronics. Okay. Thank you all. Thank you all for your patience. Bye. So tomorrow we'll be starting at 10.
ಮನೆಗೆ ಹೋಗ್ಬಿಟ್ಟು